James Webb just found a galaxy so distant its light left when the universe was only 290 million years old, and it may already contain oxygen. That is a chemical fingerprint that should take time the cosmos supposedly did not have. So what are we really seeing here? An impossible galaxy, a mistaken distance, or a crack in the timeline that sets the age and expansion of the universe? What Webb delivers is not a photograph of the past but a measurement, light sorted into wavelengths where each notch matters. In that pattern, astronomers read distance, temperature, motion, and the fingerprints of elements forged inside stars. But at extreme redshift, those fingerprints arrive stretched and faint, and the difference between certainty and illusion can be a fraction of a pixel. Oxygen is not just stuff floating in space. It is a timestamp because it must be manufactured, released, and mixed. If it appears too soon, the problem is not merely one galaxy. It is the pace of the first stellar lives and the calendar we use to date the cosmos. To understand why, we have to walk backward through the chain of inference that turns infrared light into a cosmic age. We will see how Webb's instruments isolate ancient photons and why this telescope took decades to build. We will watch how a redshift becomes a distance and how a distance becomes a time since the Big Bang by leaning on a model of expansion that has organized modern cosmology for a generation. That model is powerful because it links many kinds of evidence into one coherent picture. Yet its strength is also its vulnerability. When a measurement lands at the edge of the observable universe, small uncertainties can swell into enormous consequences. A line can be misidentified, a calibration can drift, a foreground object can masquerade as a primordial one, and a statistical fluke can look like a new era. And still the opposite possibility remains on the table, quietly, uncomfortably, and with growing interest. Perhaps the early universe was more efficient than our simulations allow, forming massive stars that lived fast and enriched their surroundings with startling speed. Perhaps the first galaxies assembled earlier, brighter, and stranger than the textbooks predicted. Or perhaps the cosmic clock itself, the one that assigns ages to the most distant light, is not as settled as it appears. So we begin with the evidence, then follow the machinery that produced it, and then confront the blueprint that translates it into history. Along the way, we will meet other early galaxies that seem too bright, too massive, or too organized for their supposed era, and we will ask whether they are mirages, rare peaks, or a genuine population. By the time we return to the original signal, you will know exactly what would need to be true for oxygen to appear so early, and exactly what would need to be wrong for it to disappear. Now settle in for a journey from Webb's infrared eye to the Lambda CDM timeline that dates the first galaxies. We will trace how one result can stress test an entire cosmological framework, and when the story reaches the Hubble tension in the next generation of surveys, the mystery will narrow, not by drama, but by better evidence. A single spectrum lands on a screen and a headline follows. Oxygen detected in a galaxy at the edge of the universe. One word shifts the entire story, because oxygen is not just chemistry. In astronomy, oxygen counts as a metal, meaning anything heavier than helium. That definition sounds strange on Earth, yet it is practical in space where hydrogen and helium dominate almost everything we see. Metals are forged inside stars, then scattered by stellar winds and supernovae. In the cores of massive stars, helium fuses into carbon, and carbon can fuse into oxygen. Those reactions require extreme temperatures and pressures, the kind only gravity can sustain for millions of years. When the star dies, its interior is no longer locked away, and the galaxy inherits the debris. Oxygen is a timestamp stamped by stellar lives and violent deaths. The claim sounds simple, but it carries a threat. This galaxy's light has traveled about 13.4 billion years to reach us. We see it as it was when the universe was roughly 290 million years old. That number is not a footnote, it is the cosmic clock reading. It places the object in an era when structure should be young, fragile, and chemically primitive. Yet the spectrum suggests maturity, and maturity requires time. To understand why this is unsettling, we need a timeline that feels real. The Big Bang sets the starting gun, then the universe expands and cools. In the first minutes, the simplest nuclei form, leaving mostly hydrogen and helium with only traces of lithium. Much later, the plasma clears and the cosmic microwave background is released, an afterglow that still fills the sky today. For a while there are no stars, only dark hydrogen and helium drifting through expanding space. That interval is sometimes called the cosmic dark ages, and it is not poetic exaggeration. Without stars there is no visible light, only cooling gas and the slow pull of gravity. Tiny density ripples seeded in the early universe begin to grow into the first dark matter halos. Gas falls into those halos, compressing and heating, then cooling again as it tries to set. The first stars ignite later, and they are thought to be massive and short-lived. Their radiation begins the long process called reionization, when neutral hydrogen becomes ionized again. Ultraviolet photons from early stars and galaxies tear electrons from hydrogen atoms, changing how the intergalactic medium absorbs and transmits light. Reionization is not a switch that flips everywhere at once. It is patchy, with bubbles of ionized gas expanding around the earliest luminous sources. Early galaxies assemble in that glare-building mass while the intergalactic medium changes state. In standard narratives, heavy elements accumulate gradually, generation by generation. The first stellar generation begins with pristine gas, then ends by polluting its surroundings. Later stars form from that enriched material, and their spectra begin to show stronger metal lines. Dust grains can also form from metals, altering how starlight is absorbed and remitted. Over time, a galaxy's chemistry becomes a record of how many stellar lives it has already spent. Now place 290 million years on that arc. It is early, even by early universe standards. It is before reionization is complete and near the dawn of the first galaxies. It is the moment when any galaxy we can see should be close to its very beginning. If oxygen is already present in notable amounts, then star formation started earlier, proceeded faster, or enriched gas more efficiently than expected, or we are being fooled by the data, by our assumptions, or by the model itself. The observational claim is anchored to a number. Redshift Z is reported around 1432, which is extreme even for James Webb. Redshift is the stretching of light as space expands, so wavelengths arrive longer than when they were emitted. The higher the redshift, the more the wavelength has been pulled toward the infrared where human eyes cannot see. In practice, that means a galaxy that once glowed in ultraviolet can show up as a faint infrared smudge. Redshift is also a distance measure because expansion accumulates over the photon's entire journey. It is also a time measure because looking far away means looking back in time. The same equation that maps redshift to distance also maps it to cosmic age once an expansion history is assumed. Faraway objects are time machines and their photons arrive as evidence on a screen. That evidence looks like a jagged line with bumps that may be real or may be noise. At Z around 14, the universe is not just distant, it is young. A galaxy there is seen before most galaxies have had time to grow large. It is seen before many models expect stable disks, complex dust, or rich metal lines. Yet the spectrum appears to show an oxygen feature, and oxygen implies prior stellar processing. That is why the word oxygen changes everything. It suggests the galaxy is not a pristine first light object. It suggests it has already lived through at least one cycle of star birth and death. Even one generation is enough to matter because massive stars evolve quickly. A star tens of times the sun's mass can burn through its fuel in only a few million years. When it explodes, it can seed its surroundings with oxygen and other elements almost immediately by cosmic standards. Here is the tension that makes the mystery. People hear oxygen and translate it into a rough intuition. Heavy elements take about 1 billion years to build up. That intuition is not a law of nature, but it captures a set of assumptions. It assumes star formation ramps up slowly in small halos because early structures are shallow and easily disrupted. It assumes enrichment is limited by how fast gas turns into stars. It assumes supernovae eject metals, but much of that material escapes shallow gravitational wells. It assumes early feedback blows gas out and delays the next generation, turning growth into a stutter rather than a surge. It also assumes we are not preferentially catching rare extreme objects in small survey volumes. Under those assumptions, strong oxygen lines at 290 million years feel too early, but the universe does not promise to follow our intuitions. A few massive stars can create oxygen quickly because massive stars live fast and die young. A burst of star formation could enrich gas in tens of millions of years, especially if the gas is dense and rapidly recycled. A dense region could trap ejecta efficiently instead of losing it to intergalactic space. A galaxy could appear chemically mature if we are seeing a compact starburst, not a settled system. The problem is not that oxygen is impossible. The problem is whether the reported oxygen is real and whether its implied abundance fits within plausible early histories. Spectral lines can be subtle, and subtlety is dangerous at the edge of detection. A line can be shifted, broadened, or blended with neighbors depending on gas temperature, density, and motion. Even the presence of ionized oxygen implies a strong radiation field, which itself tells a story about the stars. That is where the investigation truly begins. The protagonist is a galaxy, but the setting is the edge of the observable universe. The distance is not scenery. It is a filter that turns photons into clues. Those photons have crossed a changing cosmos, passing through hydrogen that can absorb specific wavelengths. Along the way, the intergalactic medium can carve away parts of the spectrum, leaving gaps that mimic intrinsic features. Every measurement is made through expansion, through intervening gas, and through an instrument with its own biases. At these redshifts, a small error in wavelength becomes a large error in age. A misidentified line can move a galaxy across hundreds of millions of years, and that shift rewrites the entire timeline. The cosmic clock is precise only if the inputs are correct. James Webb Space Telescope is the key player because it can see what Hubble could not. Webb is tuned for infrared light, where the earliest galaxies are shifted. Its mirror collects far more light than Hubble's, and its detectors are cooled to reduce their own thermal glow. Sensitivity makes faint objects measurable, and its spectrographs turn smudges into physical claims. A spectrum is not a picture. It is a ledger of wavelengths. Peaks and dips correspond to atoms, ions, and conditions in gas. When a team says oxygen, they mean a specific feature at a specific observed wavelength. They mean a line that should appear only if the galaxy's gas contains oxygen in an excited state. Yet every step from photon to headline can introduce uncertainty. The redshift can be photometric, inferred from colors, or spectroscopic, pinned by lines. Photometric redshifts can be fooled by dust, by unusual stellar populations, or by line contamination. A sharp break in brightness can mean hydrogen absorption at high redshift, or it can mean something closer with different physics. At the edge of the universe, those possibilities can look uncomfortably similar. Spectroscopic redshifts can be fooled by noise, by overlapping features, or by miscalibration. The instrument must subtract backgrounds, correct detector artifacts, and align wavelengths with extreme precision. At the edge of detectability, a few data points can dominate interpretation. The claim is bold because the signal is faint, and faint signals demand careful skepticism. The other key player is lambda CDM, the standard model of cosmology. It combines cold dark matter with a cosmological constant, and it predicts how structure grows. It sets the expansion history that converts redshift into age, and it anchors that history with measurements like the cosmic microwave background. It gives a framework for when halos collapse and when galaxies should appear. It also sets expectations for how quickly gas can cool and form stars in the first deep potential wells. If a galaxy at z equals 1432 is already enriched, lambda CDM is not automatically broken, but it may be strained. It may require rare conditions, or it may expose missing physics in early star formation. Simulations have to approximate processes that occur far below their resolution, like turbulence, radiation transport, and the way supernovae couple energy into gas. When a spectrum disagrees with the simulation, the question becomes precise. Which assumption is failing, and by how much? So the stakes are clear and they cut in three directions. First, the measurement could be wrong, meaning the redshift is lower or the line is not oxygen. Second, the interpretation could be wrong, meaning oxygen is present but not in the abundance implied, or the feature arises from another process. Third, the model could be incomplete, meaning early galaxies formed and enriched faster than our simulations capture. Each answer changes a different part of the story. One challenges the data, one challenges the inference, and one challenges our cosmology. Each possibility carries its own kind of discomfort because each forces us to admit a different weakness. Are we misreading a fragile signal? Are we overconfident in a physical translation? Or are we missing a chapter in how the first galaxies behave? The mystery is not only what the line is, but what our reaction to it reveals. We will treat those three answers as the map for this entire investigation. We will follow the photons back through the pipeline from spectrum to redshift to physical properties. We will ask what oxygen detection actually means in practice and what alternative identifications exist. We will test what kinds of early star formation histories can produce oxygen quickly without violating what we already know about the early universe. We will compare those histories to the constraints of lambda CDM and the cosmic microwave background. We will keep the cosmic clock in view because the age estimate depends on the expansion history we assume. And we will keep returning to the same central problem, a thin feature in a spectrum carrying a weight far larger than its size. For now, the mystery remains suspended on that thin line. If it is oxygen at z equals 1432, then a galaxy is speaking from an era we barely understand. If the line is not oxygen, then the episode becomes a lesson in how easily the edge of the universe can mislead us. Either way, the signal forces a confrontation with our methods and our models. To judge the claim, we have to understand the eye that saw it and the physics that shaped what it could possibly see. Webb is not just bigger than Hubble. Webb is tuned for a different universe, one where the first light arrives stretched, diluted, and faint. Cosmic expansion does not only push galaxies away, as if space were an empty stage. It also stretches the space between wave crests as photons travel, dragging their wavelengths to longer values and lowering their energy on arrival. In practical terms, ultraviolet and visible starlight can slide into infrared by the time it reaches us. A galaxy that once blazed in hot young ultraviolet can arrive as a dim infrared whisper, and that whisper is easy to miss. At redshift 14, the shift is so extreme that ordinary optical telescopes are nearly blind because their detectors are simply looking in the wrong part of the spectrum. Redshift is more than a distance label. It is also a clock because the light has been traveling since the universe was young, when galaxies were still assembling their first generations of stars. The higher the redshift, the earlier the snapshot, and the more severe the stretching of the spectrum. That stretching also spreads a galaxy's light over a wider range of wavelengths, reducing the flux in any single band. The first light is not only far away, it is redistributed into a regime where the sky and the telescope itself can compete with it. This is why infrared matters for first light, and why seeing farther is not a simple matter of magnification. The earliest galaxies are expected to be dominated by massive blue stars and ionized gas because short-lived stars form quickly and burn fiercely. Their strongest signatures begin in the ultraviolet and optical, where hydrogen and metals imprint sharp edges and bright lines. By the time those signatures cross more than 13 billion light-years, they land in the near-infrared and sometimes the mid-infrared. If you cannot measure infrared precisely, you cannot read the early universe's ledger, its ages, its star formation, and its chemical hints. Webb's wavelength range is built around that fact, and it is engineered as a deliberate bridge between regimes. It covers roughly 0.6 to 28 microns across its instruments, spanning the edge of visible red into near-infrared and out to mid-infrared. That span is not a luxury. It is the difference between seeing a high redshift galaxy's spectral break and missing it entirely, because the break can slide across filters as redshift climbs. In deep fieldwork, the ability to sample many adjacent bands is how you avoid fooling yourself. Sensitivity is the other half of the equation, and it is where the romance of first light meets harsh counting statistics. The first galaxies are not only redshifted, they are intrinsically small, distant, and often low in dust, which can make their light bluer in the rest frame but still faint in total power. Every photon matters because the signal is weak and the background is relentless. And background in infrared is not just the sky. It is also the observatory, the optics, and the detector's own noise. Webb's primary mirror is the blunt instrument of sensitivity, and its scale is easiest to appreciate when considered fully. It is 6.5 meters across, made of 18 hexagonal segments that act as one surface, like a honeycomb of gold-coated panels. A larger mirror collects more light, and more light means deeper exposures and fainter detections at the same signal-to-noise. In deep fields, collecting area becomes time saved or depth gained, and time is the currency of discovery. The mirror is coated in gold because gold reflects infrared efficiently across Webb's working range. That choice is not aesthetic. It is a throughput decision that pushes more ancient photons onto detectors rather than losing them as heat. When the target is a galaxy near the edge of the observable universe, small efficiencies compound into discovery because each optical surface is another chance to waste the signal. Segmented mirrors are not simple mirrors, and Webb's is less a single object than a controlled system. Each segment has actuators that adjust position and curvature, aligning the whole surface to nanometer precision, which is smaller than the wavelength of near-infrared light. Webb had to become diffraction limited at near-infrared wavelengths, meaning its sharpness must be limited by physics, not by misalignment or thermal drift. Without that stability, faint galaxies blur into the background and spectra lose contrast as light smears across pixels. Even the idea of focus becomes a choreography at this scale. After launch, the segments had to be identified, moved, and phased until their separate images collapsed into one coherent point spread function. That process is wavefront control, and it is the difference between a deep field full of smudges and one full of measurable galaxies. That adjustment is not metaphorical. It is the difference between a telescope that hints and one that measures. The mirror alone is not enough because infrared astronomy has an enemy that optical telescopes can mostly ignore. Anything warm glows in infrared, including the telescope itself, and that glow is not a minor nuisance. A warm observatory can drown its own targets in thermal emission, turning the instrument into a bright foreground that overwhelms the faint cosmic signal. In infrared, the telescope is always at risk of becoming the brightest thing in its own images. That is why Webb is a cold telescope, and why its silhouette is dominated by a shield that looks more like a sail than a scientific instrument. Its 5-layer sunshield blocks sunlight and earthlight, and it enables passive cooling of the optics by allowing heat to radiate away into space. The shield is made from capton, thin and reflective, with layers separated so heat leaks outward step by step rather than flooding the cold side. Each layer reduces the heat flow, and the temperature drop is the difference between signal and self-noise. Passive cooling is a design philosophy and a constraint, and it shapes everything from pointing to scheduling. It avoids heavy cryogenic tanks that would limit mission life because stored coolant eventually runs out. It also demands a stable orientation because the shield must always face the sun, keeping the telescope's cold side in permanent shade. Webb's entire observing strategy is shaped by the need to stay cold, and that need quietly dictates where it can look at any given time. The sunshield is also a risk multiplier because it is not a rigid plate but a deployable structure with little tolerance for error. It had to unfold perfectly after launch, with hundreds of release mechanisms and tensioning steps, each one a potential single point of failure. One snag could have ended the mission before the first image, leaving only engineering data and a cautionary tale. Webb's promise was always paired with fragility, an audacious design balanced on a sequence of irreversible moves. Cooling is not uniform across the observatory, and that unevenness is part of the instrument story. The near-infrared instruments operate cold enough with passive cooling because their detectors and optics can tolerate higher temperatures without being swamped by thermal photons. The mid-infrared instrument needs even lower temperatures, so it uses an active cryocooler to reach the required range. Mid-infrared sensitivity is purchased with complexity because the colder you go, the harder it is to keep the system quiet and stable. Webb's orbit is the other pillar of its design, and it is chosen for geometry as much as for distance. It does not circle Earth like Hubble. It travels to the second Lagrange point about 15 million kilometers away, where the gravity of Earth and Sun helps it maintain a stable position relative to both. L2 is not a magical parking spot. It is a region where Webb can keep Sun, Earth, and Moon on the same side behind the sunshield, so the cold side remains cold. That geometry minimizes stray light and keeps temperature steady, which matters because thermal changes can subtly distort optics and shift detector behavior. Thermal stability is observational stability, especially for long exposures where you stack hours of data and expect the instrument to behave the same way throughout. L2 also enables continuous viewing of large parts of the sky, and that continuity is a quiet superpower. Webb can stare for hours or days without Earth eclipses interrupting observations because it is not repeatedly passing into shadow. Deep fields depend on uninterrupted integration because stacking many exposures is how faint galaxies emerge from noise. At the edge of detection, continuity becomes a scientific advantage and interruptions become visible as lost depth. But L2 comes with a cost that is both practical and philosophical. It is too far for astronaut servicing with current capabilities, and the mission was never designed around routine repairs. There is no rescue shuttle waiting in the wings. Webb was built for one launch, one deployment, and then whatever the hardware can endure, which makes every design choice feel final. That permanence shaped the program's history, and it helps explain why the telescope feels like a long-delayed promise. Webb took roughly 30 years from concept to launch, pushed by technical ambition and political turbulence with milestones that often arrived later than planned. The mirror, the shield, the detectors, and the deployment sequence all carried first-of-their-kind hazards, and each hazard demanded testing, redesign, and more testing. The mission was not late because it was careless. It was late because it was trying to do something no previous observatory had ever attempted. Budget politics became part of the engineering story because large science missions live inside shifting priorities. Costs grew as requirements hardened and failures were prevented rather than fixed in space. And prevention is expensive because it must be proven. Schedules slipped because the mission could not tolerate unknowns, and unknowns hide in mundane places like wiring harnesses and hinge tolerances. The price of seeing first light was learning to fear every overlooked bolt and cable, every small thing that could stop a big telescope from unfolding. Testing became a mission inside the mission, with its own drama and its own stakes. Components were chilled, shaken, and cycled to simulate launch in space because materials behave differently when they are cold and weightless. Optical alignment was rehearsed because it could not be improvised after deployment, and because the system had to work the first time. The goal was not elegance. The goal was survival long enough to do science, and survival in space is never guaranteed. Science is ultimately done by instruments, not by mirrors, and Webb's instruments are designed to turn faint smudges into physical statements. Webb carries a suite built to measure distance, composition, and conditions, because astronomy is inference from light. Each instrument answers a different part of the same question, and together they reduce ambiguity. What is this object? How far is it? And what is it made of? NIRCam is Webb's primary near-infrared imager, and it is the workhorse for the deep field views. It takes deep images through multiple filters, building a galaxy's colors across wavelength, and those colors encode the shape of the spectrum. Those colors are not just beautiful. They are the raw material for photometric redshifts, where a distance is inferred from how the spectrum is shaped even when individual lines are too faint to isolate. Photometric redshifts rely on a key feature that acts like a cliff in the spectrum. Neutral hydrogen absorbs light shortward of the Lyman limit and strongly suppresses flux blueward of Lyman alpha, so the spectrum drops sharply at a predictable rest wavelength. As redshift increases, that sharp drop moves into redder filters, sliding step by step across NIRCam's bandpasses. A galaxy can appear to vanish in one band and reappear in the next, creating a dropout signature that points to a specific redshift range. The dropout method is powerful because it is fast, and it is dangerous because it is indirect. Dropouts are powerful but ambiguous, especially when the signal is near the noise. Dusty galaxies at lower redshift can mimic a high redshift color break because dust reddens spectra and can suppress blue light in a way that looks similar. Strong emission lines can also contaminate broadband filters, making a galaxy look more distant than it is by boosting flux in one band. Photometry is a first pass, not a verdict, and the best candidates are the ones that survive multiple consistency checks. NIRSpec is Webb's near-infrared spectrograph, built for confirmation and for physical diagnosis. It spreads light into a spectrum, letting astronomers identify emission and absorption features at specific wavelengths rather than guessing from broad colors. Those features can lock down a redshift and reveal gas conditions, including ionization and density indicators. Spectroscopy turns a candidate into a physical object with measurable lines that can be compared to models. NIRSpec's multi-object capability matters in practice because deep fields are crowded with faint sources. It can observe many targets at once using microshutters, tiny controllable apertures that open for selected galaxies and close to block unwanted light. It can also use fixed slits and an integral field unit for different science goals, from precise single-object work to spatially resolved spectroscopy. The flexibility is designed for surveys and for detailed follow-up because discovery and confirmation have different needs. MIRI extends Webb into the mid-infrared, where the universe looks different again. It can image and take spectra, where dust emission and longer wavelength lines become accessible, and where cooler components of galaxies can contribute more strongly. For the earliest galaxies, MIRI can probe rest frame optical features that have shifted beyond the near-infrared, offering another way to test a redshift. It is slower and more background limited, but it reaches a different set of diagnostics, and sometimes that difference is decisive. The fine guidance sensor stabilizes the telescope so exposures stay sharp, holding position on guide stars with extreme precision. Stability and calibration are part of the measurement, not an afterthought, because a drifting image can turn a faint line into a false one. And a false line is worse than no line because it costs time and generates misleading conclusions that must then be painstakingly retracted. With these tools, Webb does something specific, and the specificity is what makes the claims testable. It translates redshifted ancient light into measurable chemistry, and it does it by separating wavelengths cleanly enough to recognize patterns. The chemistry is inferred from spectral fingerprints, where atoms and ions emit or absorb at known rest wavelengths. When those fingerprints shift together by the same factor, distance and composition become linked in a single observation. This is where the oxygen claim lives, and it is worth being precise about what oxygen means in this context. Astronomers do not mean oxygen gas in the everyday sense, and they do not mean breathable air drifting between stars. They mean ionized oxygen producing characteristic forbidden lines, often discussed as OIII at 500, 7 nanometers in the rest frame, a transition that is strong in many star-forming regions. At extreme redshift, that line is shifted into the infrared where Webb operates, turning a familiar optical diagnostic into an infrared target. At Z around 14, even familiar lines land at unfamiliar observed wavelengths, and the numbers become startling. A rest frame optical line can move into the near-infrared or mid-infrared depending on the exact redshift, and that determines which instrument can see it. That makes line identification both possible and perilous, because a spectrum may contain only a few detectable features. When there are only a few features, each one carries heavy interpretive weight, and each one must be interrogated. Line identification has caveats at the frontier, and those caveats are not academic. Noise spikes can masquerade as lines when the signal is faint, especially if you search many wavelengths and then highlight the strongest peaks. Lines can blend if resolution is limited, or if the galaxy has broad velocity structure from outflows and turbulence. Calibration errors can nudge wavelengths enough to change which line seems to fit, and small shifts matter when you are matching patterns across a sparse spectrum. Even when a line is real, the physical inference is layered because line strength is not a single variable thermometer. OII strength depends on oxygen abundance, but also on ionization state, gas density, and the hardness of the radiation field, meaning the typical energies of the photons produced by stars. A young intense starburst can boost certain lines without requiring extreme metallicity because hot stars flood the gas with ionizing photons. Oxygen detection is a clue, not a full chemical inventory, and it must be placed in context with other lines and continuum shape. There is also a deeper implication hiding behind the word oxygen, and it is why the claim feels so dramatic. Oxygen is not made in the Big Bang in meaningful quantities, so it must be forged in stars and dispersed by stellar winds and supernovae. If oxygen is present very early, then stars must have formed, lived, and died quickly enough to enrich the gas, and that timeline becomes part of the mystery. The question is not only whether a line exists, the question is what kind of stellar population could create it so soon. Confirming a redshift is therefore a procedural battle, and the procedure is designed to reduce self-deception. First comes the photometric estimate from NIRCam colors and the dropout pattern, which narrows the possibilities but does not settle them. Then comes spectroscopy, ideally detecting multiple lines that agree on the same redshift, because agreement is harder to fake than a single feature. The more lines that agree, the less room for coincidence, and the more robust the interpretation becomes. At Z near 14. 32, confirmation is extraordinary and hard to secure, partly because the universe becomes an adversary. The Lyman alpha line is often absorbed by neutral hydrogen in the early intergalactic medium, removing an easy redshift anchor that works well at later times. That forces reliance on weaker lines or on continuum breaks, which are harder to measure when the signal is faint. The universe itself hides the simplest evidence because reionization is incomplete and neutral gas is still common throughout the early intergalactic medium. Teams must also separate the galaxy from foregrounds, and this is where the image can be misleadingly clean. A faint high redshift source can sit near brighter objects whose light leaks into the extraction, and the leakage can distort colors and spectra. Background subtraction becomes delicate because the sky and telescope contribute their own infrared glow, and because detectors have subtle systematics that must be modeled and removed. At the limit, analysis choices can shift significance, which is why independent reductions and crosschecks matter enormously. This is why Webb's engineering choices are not separate from the science claim, but are woven into it. The mirror sets the photon budget, determining how quickly the signal rises above noise. The cold design suppresses self-emission, so those photons are not buried under thermal background. The L2 orbit stabilizes temperatures and pointing, so long integrations remain coherent. And coherence is what makes stacking exposures meaningful. Every layer of Webb's design aims at one outcome. Capture redshifted first light, disperse it into a spectrum, and read the fingerprints that imply distance and chemistry. The oxygen question begins as an engineering question about whether the signal is trustworthy, and then becomes an astrophysical question about what the signal implies. In that sense, Webb is both a camera and a lie detector, though the interrogation still depends on the questions we ask. The 30-year build is part of the suspense because it created a telescope that can reach the edge and also a data set that is easy to overinterpret. Webb can see astonishingly far, but it cannot make the universe simpler, and it cannot supply missing context by itself. It delivers spectra that demand models, assumptions, and careful humility. Because the early universe is a regime where our intuitions were trained on later times. When the data are sparse and the stakes are high, caution becomes part of the scientific method. Now the story turns from hardware to interpretation. Webb gives wavelengths and fluxes, and it delivers them with exquisite stability. But those numbers are not yet history. They are calibrated counts shaped by detectors, optics, and background subtraction, still waiting for a cosmological translation. To turn light into a timeline, cosmology supplies the conversion, an agreed-upon ruler for distance, age, and growth. That conversion is lambda CDM, the standard model of cosmology. It is not a single idea and it is not a single equation, but a compact accounting of what the universe contains and how it evolves. In practice, it is a framework that ties geometry, expansion, and gravity into one coherent narrative. It also specifies how small early irregularities grow into the structured sky we actually observe. Lambda CDM says ordinary matter is about 5% of the cosmic budget. Dark matter is about 27%. And dark energy, written as lambda, is about 68%. Those fractions look like a clean accounting ledger, yet each slice carries a different physical role and the accounting is deceptively tidy. The numbers are not philosophical preferences. They are fitted parameters cross-checked across many data sets. They are constrained by patterns in the sky, not by aesthetics, so changing them is never a casual choice. When the parameters shift even slightly, the inferred ages at extreme redshift can move by tens of millions of years. Ordinary matter is the part that forms stars, gas clouds, and oxygen lines. It interacts with light through electromagnetism, cools by radiation, and clumps into the visible structures telescopes actually image. It is also the only component that can make chemistry, because chemistry requires charged particles and photons. In the early universe, it begins as a thin gas, then becomes a complicated mixture of plasma, molecules, dust, and metals as time passes and stars process it. Dark matter is the scaffolding that ordinary matter falls into. It does not emit or absorb light, but its gravity dominates the growth of structure from the earliest times. We infer it through its gravitational pull in rotation curves, in cluster dynamics, and in the subtle shear patterns of gravitational lensing. It is the invisible architecture, an underlying mass map that the glowing galaxies merely trace. Without it, the first structures would form far too slowly to match what we actually observe. Dark energy is the smooth component that accelerates expansion at late times. In the simplest version, it behaves like a constant energy density of empty space. So as the universe expands, the total amount of that energy effectively grows. That counterintuitive behavior is why it eventually overwhelms matter's gravitational pull. It does not clump into halos. So its signature is written into the global stretching of space itself, visible in the way distant supernovae appear fainter than a decelerating universe would predict. Lambda CDM became the organizing framework because it links early universe simplicity to late universe complexity. It explains why the cosmic microwave background is smooth, yet galaxies and clusters exist at all. It also explains why the universe is close to geometrically flat within measurement errors. The model's elegance is that one set of parameters must satisfy all of these facts simultaneously. Historically, this blueprint did not arrive all at once. The CDM part gained traction as galaxy rotation curves and cluster dynamics demanded unseen mass, and as simulations showed that cold dark matter naturally builds the cosmic web of filaments and voids. The lambda part returned later after supernova surveys revealed that expansion is speeding up, not slowing down. In the late 1990s, that result landed like a reversal because gravity was expected to break the expansion, not let it run away and accelerate. The discovery demanded a new ingredient in the cosmic accounting, and lambda was the simplest available answer. The cosmic microwave background is the opening snapshot in this model. It is the afterglow released when the universe cooled enough for electrons and protons to form neutral atoms, roughly 380,000 years after the Big Bang. At that moment, light decoupled from matter and began free streaming. The CMB preserves a map of tiny density fluctuations at the level of tens of microkelvin. Those temperature variations correspond to slight differences in density and velocity, minute ripples that later become enormous structures spanning hundreds of millions of light years. The CMB is also a measurement of scales. The pattern includes a characteristic angular size set by sound waves in the early plasma, and that acoustic scale anchors many cosmological parameters. It is one reason lambda CDM can convert a redshift into a cosmic age with such apparent confidence. The peaks in the CMB power spectrum act like a ruler, one that has been checked and rechecked across multiple independent experiments spanning decades of observations. Those fluctuations are the seeds of everything that follows. In lambda CDM, gravity amplifies them over billions of years, turning slight overdensities into halos and filaments. The process is slow at first, then increasingly dramatic as small advantages in density compound over time. A region that is only slightly denser than average can, given enough time, become the birthplace of a galaxy cluster containing thousands of individual galaxies. That compounding is the engine of cosmic structure. The model's power comes from how much is fixed by that snapshot. Given the CMB pattern and a few parameters, the later distribution of matter becomes highly constrained. In other words, the early universe is like an initial condition file. Change it and the entire later movie changes. That is why the CMB is so central. It limits how creative we can be about the later story, and it punishes models that grow structure too fast or too slow by leaving telltale fingerprints in statistics we can measure. Cold dark matter is the key assumption about the invisible component. Cold means the particles move slowly compared to the speed of light when structures begin to grow. That coldness is not about temperature in a household sense, but about momentum and free streaming length. The slower the particles, the less they erase small-scale density features by streaming out of them. Slow particles allow small clumps to survive, collapse early, and then merge into larger structures as time passes. If dark matter were hot, fast-moving particles would wash out small-scale structure, and the first galaxies would form later and differently. Even warm dark matter would subtly soften the smallest halos, changing the predicted abundance of early star-forming sites. This is not a trivial distinction because the abundance and mass of early halos directly controls how many high-redshift galaxies should exist and how quickly they can grow. This is the hierarchical picture. Small halos form first, then merge into bigger halos, and galaxies assemble through accretion, mergers, and repeated episodes of star formation. Hierarchical growth is not just a conceptual framework. It is a quantitative expectation that shows up in simulations, in halo mass functions, and in how clustering evolves with redshift. It also appears in statistics like the correlation function, which measures how strongly galaxies cluster at different scales. In lambda CDM, those statistics are not decorative. They are tests that punish models that grow structure too fast or too slow. Baryons, the ordinary matter, ride on that dark matter backbone. Gas falls into halos, heats by shocks, cools by radiation, and sometimes forms stars if conditions allow. The gas must also shed angular momentum because rotation can support it against collapse even when gravity is strong. In early halos, a little extra heat or turbulence can decide whether gas settles into a disk or never settles at all. And in the early universe, those conditions are particularly hard to satisfy. Small halos have shallow gravity, and early star formation can be disrupted by radiation and supernova feedback. A single generation of massive stars can heat and expel gas, temporarily shutting down the very process that created them. The first galaxies are therefore expected to be intermittent, lighting up, fading, then lighting up again as gas cools and reaccretes. Cooling is the bottleneck, and cooling depends on microphysics that simulations must approximate rather than resolve directly. Primordial gas lacks metals, so it relies on hydrogen and helium lines and on molecular hydrogen, which is fragile under ultraviolet light. If molecules are destroyed, the gas stays warmer, and warmer gas resists fragmentation into many small stars. In plain terms, hot gas is puffy, and puffy gas does not break into dense star-forming clumps easily. That is why lambda CDM tends to predict a slow buildup of mature galaxies, with the first objects expected to be small, bursty, and chemically primitive. The timeline implied by lambda CDM begins with recombination and the CMB, then a long period with no stars, where neutral hydrogen dominates and the only light is the fading afterglow. Structure grows invisibly in dark matter while baryonic gas cools only gradually and struggles to fragment efficiently. Gravity is working, but the universe has not yet built the luminous signposts we use to track its progress. Then the first stars ignite, often labeled population III. They are expected to form from pristine hydrogen and helium with no metals to help cooling. With inefficient cooling, the first stars are often modeled as massive, much more massive than typical stars today. Massive stars burn hot, live briefly, and end as supernovae or direct collapse black holes depending on mass. Their lifetimes can be only a few million years, which is cosmologically instantaneous. In that short span, they can flood their surroundings with ionizing photons and begin altering the chemistry of the next stellar generation. Those first stars trigger the next phase. Their ultraviolet radiation begins reionization, the process that reionizes neutral hydrogen in the intergalactic medium. Reionization matters because it changes the transparency of the universe and alters how gas accretes into small halos. Once the background becomes more ionized, small halos can struggle to hold onto gas because heated gas has more pressure support against gravity. Gas that cannot fall in is gas that cannot make stars. Reionization is not instantaneous. It proceeds in patches, with ionized bubbles growing around early galaxies and quasars, then overlapping as sources multiply. The boundary between neutral and ionized regions is not a clean wall. It is a ragged frontier shaped by density, radiation, and time. As ionized regions expand, the remaining neutral hydrogen becomes harder to find, yet it leaves distinctive fingerprints. It can absorb background light, carving troughs and breaks into spectra, and it can damp certain emission features. Even without seeing the gas directly, we can infer its state from what it blocks. The first galaxies emerge within that transition. They form in the earliest halos that are massive enough to hold gas against heating and feedback. Their growth is a contest between gravity pulling inward and radiation and explosions pushing outward. In this sequence, 290 million years after the Big Bang is extremely early. It sits near the onset of widespread star formation and well before reionization is complete. A mature-looking galaxy at Z around 14 therefore feels provocative because it seems to appear not at the beginning of the story, but after several chapters have already happened. To see why oxygen matters in this context, we need the basics of chemical evolution. Big Bang nucleosynthesis produces mostly hydrogen and helium with only trace lithium. The early universe is therefore chemically simple, and that simplicity is one of lambda CDM's cleanest starting conditions. It also means that any heavier element we detect at high redshift must have been manufactured locally inside stars after the first collapse. There is no other source. Oxygen is not made in meaningful amounts in the Big Bang. Oxygen is forged later inside stars through helium burning and subsequent fusion stages in massive stellar cores. In the final phases, layered shells of fusion build heavier nuclei, and oxygen becomes one of the dominant products. The stars that make oxygen fastest are also the ones that die fastest. When massive stars die, they eject newly made elements. Supernovae and stellar winds push oxygen into surrounding gas where it can later be ionized and emit lines. Yet the mixing is uneven at first, and bright knots of enriched gas can coexist with large volumes that remain almost pristine. Enrichment therefore requires time and repetition. Gas must turn into stars must evolve, explosions must distribute metals, and the metals must mix into star-forming regions. Each step has its own timescale, and the slowest step often sets the pace. The clock is not only stellar lifetimes. It is also the time it takes for enriched material to cool, settle, and participate in the next round of star formation. These cascading delays are why oxygen appearing at 290 million years feels compressed. The oxygen line often discussed in early galaxies is OIII, a forbidden transition of doubly ionized oxygen. Forbidden does not mean impossible. It means the transition is unlikely and occurs in low-density gas where collisions are rare. That detail matters because line strength depends on the physical state of the gas, not only on how much oxygen exists. In nebular conditions, OII can become a spotlight, bright when the ionizing radiation is intense and the electron temperature is high. So when people say oxygen implies at least 1 billion years, they are compressing several assumptions into one number. It assumes a typical initial mass function, often similar to later epochs. It assumes many stars are low mass and long-lived, so enrichment builds gradually across multiple generations. If instead early star formation favors massive stars, the enrichment curve steepens dramatically, and oxygen can appear quickly, while the long-lived stars that dominate later galaxies have barely begun to form. It assumes star formation efficiency is modest in small halos. It assumes feedback expels gas and delays the next burst, lowering the net rate of chemical buildup. In early shallow potential wells, a single energetic event can remove the very fuel needed for continued enrichment. The same feedback that makes oxygen can also scatter it, throwing metals into the intergalactic medium instead of keeping them in the next star-forming cloud. That escape is a real possibility in small early systems. It assumes metals mix on timescales comparable to dynamical times. It assumes the oxygen we observe traces the bulk gas, not a small region dominated by a recent event. If we are seeing a compact, intensely irradiated pocket, the spectrum may exaggerate how mature the whole system is. A single bright HII region can dominate the light even if the surrounding galaxy is still chemically young. The representative volume that a spectrum actually captures can be surprisingly small and unrepresentative. It also assumes we are not seeing an extreme outlier. In a small survey volume, the first rare peaks can dominate what we detect even if they are not typical. The earliest massive halos are statistical flukes, rare but not forbidden, and they can bias our first impressions. The first objects we find are not necessarily the first objects that exist. They are the first objects bright enough to announce themselves, and there is no guarantee that announcing objects are average objects. Lambda CDM has room to maneuver inside those assumptions. It can accommodate bursts of star formation that convert gas rapidly, especially in unusually massive early halos. In that picture, a galaxy's apparent maturity is not a slow accumulation, but the aftermath of a short, intense episode. The light we see could be the flare of a brief starburst caught at exactly the moment when nebular lines are strongest. It can accommodate a top-heavy initial mass function in primordial conditions. If most early stars are massive, then oxygen production is fast and the delay time shrinks. The same choice also increases ultraviolet output, which can strengthen ionization-driven lines like OIII. It can accommodate rapid enrichment from very massive stars that live only a few million years. A single intense burst can seed oxygen quickly, at least locally. The question then becomes whether the oxygen spreads into the regions that dominate the observed emission, and it can accommodate the fact that strong OIII emission does not require high metallicity. Line strength depends on ionization, density, and radiation hardness, not only abundance. A hard radiation field can push oxygen into higher ionization states, and high electron temperatures can make certain lines bright even at low oxygen content. But lambda CDM is not infinitely flexible. The expansion history is tightly constrained by the CMB and related measurements, and that history sets the age corresponding to z equals 14. 32. If you change the clock, you must also change the CMB-derived ruler that the clock is built from. The matter content is also constrained. The amount of dark matter and baryons affects how fast structures grow, and those parameters are not free to drift arbitrarily. Too much early structure would imply a different growth rate, which would leave imprints in lensing statistics and in the CMB itself. The CMB-derived parameters lock in a baseline prediction for early halo abundance. If too many massive halos appear too early, the model must reconcile that with the CMB map. The CMB is not just a picture of the past. It is a contract that later structure must honor. The contract is statistical, not deterministic, but it is still strict enough to make surprises meaningful and worth investigating carefully. This is where the notion of tension enters. In cosmology, tension means different datasets prefer parameter values that cannot all be true within one model. It is a technical word, but it carries a narrative charge because it signals that our crosschecks are doing their job. The point is not drama for its own sake. The point is that precision creates the possibility of disagreement. Tension is not a headline about failure. It is a diagnostic that the web of crosschecks is pulling in different directions, forcing us to inspect assumptions and systematics. The Hubble tension is the best-known example, where early and late universe measurements disagree on the expansion rate. It is a reminder that even a successful blueprint can have stress points. When the stress persists, it raises a quiet question. Are we missing a subtle systematic or a subtle piece of physics? The oxygen at Z14 claim is not the same kind of tension, but it rhymes with it. It pits an early-time observation against a timeline anchored by early-time physics. It also tests whether our recipes for early star formation are realistic or merely convenient. If the recipes are wrong, the fix might be astrophysical rather than cosmological, but the data will not tell us that automatically. If the galaxy is truly at z equals 14, 32, then its age is set by the lambda CDM ruler. If its spectrum implies significant oxygen, then its internal history must be extremely compressed. The universe would have had to build stars, make metals, and reorganize gas with astonishing speed, and it would have had to do so while the surrounding intergalactic medium was still in the middle of changing phase. That compression can be achieved in some scenarios, but not in all. The question becomes whether the required star formation and enrichment are plausible or whether the blueprint is missing ingredients. And behind that is a more unsettling question. How often do we mistake brightness for maturity? A young system in a violent starburst can look older than it is simply because it is temporarily overexposed in emission lines that imply processing without actually proving extended histories. One missing ingredient could be astrophysical, not cosmological. Simulations approximate star formation, feedback, and radiation transport, and early conditions may amplify those uncertainties. When resolution is limited, subgrid models decide how gas turns into stars, and those choices can shift predictions by large factors. Even the escape fraction of ultraviolet photons, how easily radiation leaks out, can change the ionization state that sets line strengths. In other words, two simulations with the same cosmology but different subgrid recipes can predict dramatically different early galaxy populations. Another missing ingredient could be observational. A single line can be misidentified, a redshift can be biased, and a noise feature can masquerade as a detection. At extreme distances, even small calibration errors can move a feature enough to change the story. The spectrum is faint, the background is complex, and the stakes are high, so every reduction choice matters more than it would in a routine observation of a nearby, well-characterized object. A third possibility is that the cosmological conversion from redshift to age is slightly off. That would imply changes to expansion history, which would ripple into many other constraints. Any such change must still preserve the CMB's acoustic pattern, the large-scale distribution of galaxies, and the success of gravitational lensing tests. The blueprint can bend, but it cannot break its own foundation without consequences elsewhere that we would surely have noticed by now. The reason this feels troubling is that lambda CDM's success is built on coherence. It is powerful because it makes many predictions at once, and those predictions usually agree. When coherence holds, a spectrum becomes more than data. It becomes a timestamp. The universe starts to feel readable, as though light itself carries a reliable date stamp across billions of years. A mature early galaxy threatens that coherence because it targets the model's most distinctive expectation. Structure should assemble hierarchically, and maturity should be rare at the beginning. If maturity is common, then either the growth is faster than expected or our indicators of maturity are misleading. The deeper issue is not one galaxy, but what it would imply about the whole early population. So the tension is not only about oxygen. It is about the pace of growth, the efficiency of early star formation, and the reliability of the cosmic clock we use. It is also about interpretation, whether we are reading the spectrum as a biography when it might be a snapshot of a single dramatic moment. In the early universe, a brief moment can dominate what we see because everything is compact and intensely luminous when it first ignites. Now return to the specific galaxy and its reported redshift. The number Z equals 14. 32 is not just distance. It is a claim about the universe's age at a mission. It is also a claim about how much the universe has expanded since that light began its journey. Redshift is a stretching of wavelength, but it is also a stretching of context, because it ties a single spectrum to the entire expansion history. A tiny bump in a spectrum can become a headline, but only if the chain of inference holds. From here, the chain must be reconstructed step by step. Photons become a spectrum. The spectrum becomes a redshift. The redshift becomes an age, and the lines become chemistry. Each step sounds straightforward, yet each step depends on modeling choices that can subtly steer the conclusion. The chain is strong when many features agree, and it is fragile when one feature carries the weight of the whole claim. The next chapter follows that chain and asks where the claim is strongest and where it can still slip. The goal is not to dismiss the result, but to locate exactly where uncertainty lives. In science, that location matters because it tells us what to measure next and what to doubt first. We began with an oxygen feature that seems too early. Now we have the blueprint that makes it feel too early and the constraints that make the feeling testable. The blueprint is not a fragile theory, but it is a precise one, and precision is what makes anomalies meaningful. If the anomaly survives, it does not merely add a detail, it forces a recalibration of expectations. At the edge of the universe, faraway light becomes a forensic record. If Webb's earliest galaxies truly carry oxygen so soon, then either stars lived fast or the blueprint needs revision. And if the blueprint needs revision, we must ask which part bends first, the astrophysics, the observations, or the cosmic clock itself. Now return to the specific claim and rebuild it from the rawest measurement. A faint infrared source is flagged in deep imaging, then promoted into a candidate with a number attached. That number is Z equals 14, 32, and it is both a distance proxy and a time claim. The first step is deliberately unromantic because astronomy starts with counting photons. The detector records electrons freed by incoming light, and the pipeline turns those counts into calibrated flux. Behind the scenes, bias frames, dark current maps, and flat fields are applied so that the final image reflects sky, not electronics. At these limits, the difference between real and noise can be a handful of photons spread over hours of integration. The image looks smooth from afar, but zoom in and it becomes grainy, like mist lit by moonlight where structure is suggested but never quite confirmed. Even the background has structure, with subtle gradients that can tilt a measurement if they are not modeled and removed with care. A single pixel is never the point because the telescope's point spread function distributes light into a small pattern. The candidate is therefore measured with apertures and point spread function fitting, and each choice changes the inferred flux by a small amount. Those small amounts matter because the signal-to-noise ratio hovers near the threshold where false positives begin to breed. When a source is this faint, the uncertainty is not just statistical. Systematic effects start to dominate. The question becomes uncomfortably basic. Are we measuring the galaxy or measuring our own reduction choices? That question sounds harsh, but it is the correct question to ask, and the history of high redshift astronomy is full of cases where the honest answer turned out to be the latter. Candidates that looked solid in one pipeline dissolved in another, and sources that survived multiple independent reductions are the ones worth building stories around. Redshift is wavelength stretching caused by cosmic expansion, not a Doppler shift through static space. Space itself grows and light traveling through it is stretched along the way. This is why the same galaxy can be described, without implying it is racing through a fixed void. The scale factor is 1 divided by 1 plus z, so at z equals 14. 32, the universe was about 1/15 its current size. In plain terms, every cosmic ruler was shorter, and every region was denser. Matter was also more tightly packed into filaments, and the density contrasts between overdense and underdense regions were smaller in absolute terms, even as they were large relative to the mean. Every spectral feature is shifted by the same factor, so a rest wavelength becomes about 15, 32 times longer at the detector. A line emitted in the ultraviolet can arrive as near infrared, and an optical line can drift into wavelengths our eyes never see. That simple multiplication is the heart of the claim, and it is also the trap. If the factor is wrong, then every downstream inference, age, mass, and chemistry, tilts with it. The drama of z equals 14. 32 is therefore not the number itself, but the cascade of consequences it triggers every time someone accepts it as given. That stretching is why Webb matters, because the early universe speaks in infrared by the time it reaches us. The telescope is not merely bigger than its predecessors. It is tuned for this translation. Its gold-coated mirror gathers faint light, while its cold instruments suppress their own thermal glow. Ultraviolet starlight and optical nebular lines slide into near-infrared bands where background and calibration become decisive. The background is not empty, because zodiacal light and instrument noise add a soft haze that varies with position and time. The detectors also carry signatures of their own history, persistence effects, hot pixels, and subtle striping that must be corrected without accidentally removing real signal in the process. Calibration is not a footnote because tiny errors in flat fields or dark current can mimic faint structure. The signal is faint and the inference chain must be checked link by link. The mystery lives in that chain, each step plausible, yet each step vulnerable. Redshift becomes a look-back time only after we choose a cosmological model. The universe does not hand us a clock. We build one from parameters, and under lambda CDM, parameters consistent with the CMB place Z around 14.3 at roughly 290 million years after the Big Bang. That number is startling because it compresses everything we know about galaxy building into a brief cosmic dawn. It is also conditional because the mapping from Z to time depends on the expansion history we assume. In other words, the same observed spectrum can imply slightly different ages depending on which cosmic ruler we adopt. Change the Hubble constant or the matter density and the age shifts, which is why the conversion is never model-free. Even within lambda CDM, small parameter changes move the answer by millions of years. Millions of years may sound generous, but at this epoch it can decide whether one or two stellar generations fit inside the available time. The difference between one burst of enrichment and two is the difference between a plausible early history and an implausible one. The discovery pipeline begins with deep multiband imaging, usually from NIRCam. Webb stares for hours, sometimes days, collecting exposures that are later stacked. Each exposure is dithered so the target falls on different pixels and detector quirks average out. The deep field is a tapestry of tiny smudges, arcs, and points, each one a different distance. The human eye sees beauty, but the algorithm sees measurements, fluxes, uncertainties, and correlations. What looks like a serene patch of sky is in practice a matrix of probabilities, each entry connected to every other through calibration assumptions and model choices. Astronomers search for a dropout pattern where flux vanishes blueward of the Lyman break. This break is not a property of the telescope. It is a physical cutoff created by hydrogen absorption. Neutral hydrogen in the galaxy and the intergalactic medium absorbs short wavelength light, creating a sharp step in the observed colors. The physics is atomic and unforgiving because hydrogen's cross-section rises steeply at the Lyman limit. In effect, the universe itself draws a boundary in the spectrum, and we use that boundary as a ruler. That ruler is powerful, but it becomes blunt when the data are sparse, and when the intergalactic medium is not uniformly neutral. A high redshift candidate appears in redder filters and disappears in bluer ones. That disappearance is the clue, but it is also an invitation to overinterpret. At the detection limit, disappears can mean truly absent or merely buried beneath noise. A single upward fluctuation in a red filter paired with a downward fluctuation in a blue one can sketch a break that is not really there. The pattern can emerge from statistics rather than from physics, and statistics do not care about cosmology. They simply fluctuate, and in large enough surveys, they will eventually produce any pattern by chance. Photometric redshift codes fit templates to the measured colors and return a probability distribution. The templates encode expected galaxy spectra, including breaks and emission lines, then compare them to the observed fluxes. At the frontier, that distribution can be broad, multi-peaked, and sensitive to small photometric systematics. A tiny shift in one filter's flux can move the preferred redshift by whole units. The output is not a single answer, but a landscape of possibilities. The most honest plots show that landscape, with the exciting high redshift peak sitting beside quieter lower redshift alternatives. The honest interpreter reports both peaks and explains why the high redshift solution is preferred without pretending the alternative has vanished. The next step is to ask what could fake the dropout. This is where the romance of first light meets the discipline of skepticism. Brown dwarfs in the Milky Way can mimic red colors with molecular absorption bands. Their atmospheres contain water and methane features that carve out parts of the spectrum, producing a false step. In a deep field, a nearby faint star can masquerade as a distant galaxy, an imposter hiding in plain sight. Historically, this kind of confusion has haunted surveys from early photographic plates to modern infrared catalogs. The morphology can help because true galaxies are often resolved or at least slightly extended, while stars remain point sources. But at the detection limit, morphological discrimination becomes uncertain because the signal is too faint to characterize shape reliably. Dusty galaxies at intermediate redshift present a more insidious problem. A galaxy at redshift 2 or 3, heavily obscured by dust, can have its ultraviolet light almost completely suppressed, leaving only red infrared emission. Its colors can then resemble a high redshift dropout, even though it is nowhere near the edge of the observable universe. Dust reddening mimics the Lyman break in broadband photometry because both phenomena suppress blue light, and the two effects can be difficult to separate without spectroscopy or very detailed multiband modeling. The imposter is particularly dangerous because dusty galaxies are common, and because dust properties can vary in ways that make modeling inexact. Extreme emission line galaxies are another class of imposters. A galaxy at modest redshift with unusually strong emission lines can have those lines contaminate specific filter bands, boosting flux in those bands while the true continuum level is low. The result can look like a stepped spectrum, even though the source is relatively nearby. Certain combinations of filters and emission lines can conspire to create a photometric signature that resembles a Lyman break when it is actually a set of bright, narrow features scattered across the wavelength range. These cases require spectroscopy to untangle because photometry alone cannot always distinguish a continuum break from a pattern of emission lines. Even after photometric vetting, the candidate must face spectroscopy. This is the step that separates plausible from confirmed. Spectroscopy disperses the light into a detailed wavelength versus flux plot where individual lines can be identified. In the ideal case, multiple lines appear at wavelengths consistent with one redshift, and the consistency is the confirmation. In practice, the ideal case is rare at extreme redshift because the source is faint, and many potential lines are shifted into regions where the atmosphere, instrument, or background is challenging. At Z around 14, the strongest rest frame ultraviolet lines like Lyman alpha are deeply suppressed because the intergalactic medium at that epoch is largely neutral. Neutral hydrogen absorbs those photons before they can reach us, effectively erasing the easiest spectroscopic anchor. That forces the confirmation to rely on other features, either weaker ultraviolet lines or the continuum break itself measured at high spectral resolution. Weaker lines are harder to detect because they require longer integration times or higher signal-to-noise ratios. The break measured spectroscopically is more reliable than the photometric version, but still requires careful treatment of the noise and the background. When a line is tentatively detected, the identification process is itself a kind of investigation. At a given observed wavelength, multiple transitions from different elements at different redshifts could in principle produce a peak. The choice among them is guided by which redshift is most consistent with the photometric estimate, which identification is physically plausible given the expected spectrum, and whether any additional features can be detected at wavelengths predicted by the preferred solution. The process is layered with prior knowledge and physical reasoning, and that layering introduces the possibility of confirmation bias. If the team expects a high redshift galaxy, they may be more lenient with a marginally significant line that fits the preferred solution than with one that points elsewhere. The oxygen feature specifically is a case study in this layering. The OIII doublet at 4959 and 5007 angstroms in the rest frame is one of the strongest emission lines in star-forming galaxies. It is routinely detected in galaxies at low and intermediate redshift, where it serves as a reliable metallicity and ionization indicator. At Z around 14, the 5007 angstrom line would be observed at roughly 76 microns if the redshift is taken at face value. That wavelength falls in the mid-infrared, well beyond NIR specs range and into MIRI territory. If the feature is instead closer to 10 or 12 microns, the redshift implied would be lower, and the galaxy would be younger in observed terms but older in physical terms, because a lower redshift means more time has passed since the Big Bang in lambda CDM. The exact wavelength of the claimed feature therefore matters enormously, and the claimed wavelength depends on the wavelength calibration of the spectrograph. Wavelength calibration is performed using known emission lines from calibration sources or from well-understood sky features, and any systematic offset in that calibration propagates directly into the inferred redshift, at the precision needed to distinguish Z equals 14, 32 from Z equals 13. 5. The calibration requirements are stringent. A shift of a few tens of angstroms in observed wavelength can move the inferred redshift by a significant fraction, and that fraction can decide whether the galaxy fits within lambda CDM's expectations or challenges them. Signal-to-noise ratio is the other constraint that shapes what can be claimed. A spectral feature is typically considered significant when it rises above the noise by a factor of 5 or more, often written as 5 sigma. But that threshold is not a guarantee of reality. It is a statement about the probability that pure noise would produce such a peak at that specific wavelength. When many wavelengths are searched simultaneously, the probability of finding a spurious 5 sigma peak somewhere in the spectrum rises with the number of independent resolution elements examined. This is the look-elsewhere effect, and it is particularly dangerous in high redshift spectroscopy, where automated searches examine thousands of wavelength channels looking for anything that rises above the floor. The correction for the look-elsewhere effect can be substantial. A feature that looks highly significant in a single channel can become marginal or insignificant when the full search space is accounted for. Teams that correct for this properly and then still find a significant detection are on firmer ground. Teams that report the raw peak significance without accounting for search width are providing incomplete information. The distinction matters for interpreting whether the claimed oxygen feature is a true detection or a statistical fluctuation that happened to land at a suggestive wavelength. Independent verification is the strongest form of evidence because different groups using different pipelines and different approaches to background subtraction should converge on the same answer if the signal is real. When independent teams agree, confidence rises substantially. When they disagree, the disagreement is itself informative. It points to specific steps in the analysis where the answer is sensitive to choices that should not matter but apparently do. Those sensitivities are the places where the next round of investigation must focus. The broader context also matters. Webb has now observed enough early universe candidates that statistical patterns are beginning to emerge. Individual detections at extreme redshift are impressive but inconclusive. Populations of such objects carry more weight because a single unusual detection could be noise or a rare event, while a consistent population suggests a systematic physical reality. If multiple galaxies at Z around 14 show similar spectral properties, the probability that all of them are misidentified lower redshift objects or statistical flukes decreases rapidly. Population studies also reveal whether the oxygen feature is common or exceptional among early galaxies, which constrains models in ways that single detections cannot. At the same time, populations can be systematically biased. Survey strategies that favor bright objects will find bright objects. If the brightest early galaxies happen to be the ones with the strongest emission lines and the most advanced chemistry, the sample will make early chemical enrichment look more common than it actually is. The completeness of the survey, meaning what fraction of all galaxies in a given volume and luminosity range have been detected and characterized, is a critical piece of information that is often difficult to establish precisely at extreme redshifts. Incompleteness can bias almost any conclusion drawn from high redshift samples. The case of the oxygen line is therefore not simply a question of whether a bump in a spectrum is real. It is a question of what a real bump means, given the full chain of inference from photon to claimed chemistry. That chain passes through detector physics, background subtraction, wavelength calibration, line identification, redshift confirmation, physical modeling of the emission process, and finally comparison with cosmological expectations. Each link adds uncertainty. The total uncertainty at the end of the chain is not the sum of the individual uncertainties because they interact in complex ways, sometimes reinforcing each other and sometimes partially canceling. But the total uncertainty is always larger than any single component, and it is often larger than the stated error bars suggest. This is not a criticism of the researchers who made the claim. It is a description of the regime they are working in. High redshift astronomy at the edge of detection is always a negotiation between ambition and evidence. The ambition is necessary because reaching further than the previous generation is how the field advances. The evidence is always incomplete because the universe is not obligated to be bright enough for our current technology. The negotiation is what produces science, as opposed to either timid caution that finds nothing new or reckless enthusiasm that finds everything and confirms nothing. What makes the oxygen claim particularly interesting is not just the claimed chemical maturity. It is the combination of that claim with an extreme photometric redshift. Each element of the claim would be remarkable on its own. Together, they create a compound claim whose probability of being simultaneously correct is lower than either element alone. That is not a reason to dismiss the claim. It is a reason to demand correspondingly strong evidence for both elements independently. A redshift as extreme as 1432 requires confirmation that is robust against all the alternative identifications discussed above. An oxygen detection at that redshift requires a line identification that survives alternative wavelength solutions and noise characterizations. Both requirements are demanding, and meeting them at this frontier takes time, additional data, and community scrutiny. The history of high redshift record holders is instructive here. Each new record has been set by an object that initially generated excitement and skepticism in roughly equal measure. Some records have stood and been confirmed by independent observations. Others have been revised downward when better data arrived. The revision is not a failure of the field. It is the field working correctly. Candidates are proposed, scrutinized, and either confirmed or corrected. The process is slow when the objects are faint because better data requires more telescope time, which is scarce and competed for. But the process is reliable in the long run because physics does not change and systematic errors eventually reveal themselves through inconsistencies. In this climate, the oxygen claim at Z around 14 occupies a specific position. It is a serious claim made by serious researchers using the most capable telescope ever built. It is also a claim at the very edge of what is currently measurable, which means the uncertainties are large enough to encompass both a genuine discovery and a series of compounded errors. Responsible evaluation requires holding both possibilities simultaneously, which is intellectually uncomfortable but scientifically necessary. The discomfort is productive because it motivates the follow-up observations that will eventually settle the question. Those follow-up observations will take multiple forms. Additional spectroscopy with longer integration times can improve the signal-to-noise ratio on the putative oxygen line and search for additional features that should accompany it if the identification is correct. Different instruments can be used to check whether the feature appears at the same wavelength in independent datasets. Gravitational lensing magnification, if the galaxy happens to lie behind a massive cluster, can amplify the signal enough to make fainter features detectable. And eventually, the next generation of even larger ground-based telescopes like the Extremely Large Telescope will be able to observe these objects with spectral resolution and sensitivity that exceed even Webb's remarkable capabilities. Until those data arrive, the oxygen claim sits in a state of productive uncertainty. It is neither confirmed nor refuted. It is a hypothesis that has survived initial scrutiny, but has not yet survived the full battery of tests that would make it a fact. In cosmology, that state is common for the most interesting objects and results. The history of the field is littered with objects that spent years in this liminal state before finally resolving into clarity. Some resolved into landmark discoveries, others dissolved into systematic errors. The oxygen galaxy at Z around 14 will eventually join one of those categories, and the journey toward resolution is itself a lesson in how science handles the extreme. The pipeline that turns photons into a headline is therefore both a triumph of engineering and a source of vulnerability. The engineering is triumphant because Webb genuinely can collect photons from galaxies that existed when the universe was only a few 100 million years old. That capability was not a given. It was earned through decades of design, testing, and careful operation. The vulnerability arises because at the edge of detection, the pipeline must make choices that cannot be fully validated against external standards. There is no independent measurement of the galaxy's true redshift or composition. There is only the spectrum, and the spectrum must be both the evidence and the test of the evidence. This is the fundamental epistemological challenge of extreme observational astronomy. We are using one instrument and one set of methods to both observe and confirm the observation. The only partial escape from this circularity is to use different instruments, different methods, and different analysis teams that can check each other's work. Webb provides multiple instruments that can contribute to this cross-checking. NIRCam provides photometric constraints. NIRSpec provides spectroscopic confirmation. MIRI can probe longer wavelengths and different physical diagnostics. When all three instruments tell a consistent story about the same object, confidence rises substantially. When they disagree, the disagreement is a signal that something in the analysis needs attention. The oxygen claim at Z around 14 is most credible when it is embedded in a consistent multi-instrument picture. A photometric redshift from NIRCam that is robustly preferred over lower redshift solutions, combined with a spectroscopic line from NIRSpec at the wavelength predicted by that photometric redshift, and further supported by MIRI photometry that is consistent with the expected continuum shape at the inferred redshift, is a much stronger case than any single element alone. The degree to which that multi-instrument consistency has been achieved for this specific object is the critical question, and it is a question that the community is actively working to answer. The broader population of Webb's high redshift discoveries provides context that is difficult to evaluate from any single object. Within the first year of Webb observations, a striking number of galaxy candidates were reported at redshifts that would have been considered extraordinary before the telescope launched. Some of these candidates have since been spectroscopically confirmed at high redshifts, though often at somewhat lower redshifts than the initial photometric estimates suggested. The pattern of photometric estimates being revised downward is consistent with known biases in photometric redshift methods at the detection limit. It is also consistent with the possibility that a population of very bright early galaxies genuinely exists at extreme redshifts, but is somewhat less extreme than the first measurements implied. That pattern matters for interpreting the oxygen claim because it suggests that the most reliable approach is to treat the photometric redshift as an upper envelope and wait for spectroscopic confirmation before drawing strong physical conclusions. The physical conclusions, specifically about chemical enrichment and stellar population age, are most sensitive to the exact redshift because a difference of even 1 unit in redshift at Z, around 14, corresponds to tens of millions of years of cosmic evolution. And tens of millions of years can decide whether one stellar generation fits in the available time or whether the history must be compressed beyond what simple models allow. To summarize the chain of vulnerability, the oxygen claim rests on a photometric redshift that may be systematically biased toward high values. It rests on a spectroscopic feature whose wavelength determines the identification and whose significance may be affected by the look-elsewhere effect. It rests on a physical model that connects line strength to oxygen abundance in ways that depend on gas conditions that are not independently measured. And it rests on a cosmological framework that converts the inferred redshift into an age that makes the detection surprising. Each of these links can be tested, and testing them is the work that is now underway. The result of that testing will be one of 3 broad outcomes. The redshift and the oxygen identification are both confirmed, in which case early chemical enrichment is a real phenomenon that demands explanation within the framework of early galaxy formation. The redshift is confirmed, but the oxygen feature is reinterpreted as something else, in which case the galaxy is genuinely extreme in its distance, but not necessarily in its chemistry. Or the redshift itself is revised downward, in which case the galaxy joins the large population of moderately high redshift systems that are unusual but not unprecedented. Each outcome teaches something different, and none of them is a failure of science. They are all examples of science doing what it is designed to do, which is to test claims against evidence and revise conclusions when the evidence demands it. With the measurement chain established and its vulnerabilities mapped, the question shifts from whether the signal is real to what it would mean if it is. The physical question behind the oxygen claim is about the pace of early star formation and chemical enrichment. How fast can a galaxy build oxygen from scratch, starting with pristine hydrogen and helium, and what conditions are needed to compress that process into less than 300 million years? The answer begins with the initial mass function, the distribution of stellar masses that emerge from a collapsing cloud of gas. The initial mass function determines how much of the newly formed stellar mass is in massive stars, which produce oxygen quickly and die explosively, versus how much is in low-mass stars, which live for billions of years and contribute relatively little to early chemical enrichment. The initial mass function is one of the most important and least understood quantities in early galaxy physics, and it has the power to dramatically change enrichment timescales. In the Milky Way and nearby galaxies, the initial mass function has a characteristic shape that peaks at roughly a solar mass and declines steeply toward higher masses. In this environment, massive stars are rare relative to low-mass stars, and their contribution to chemical enrichment is diluted by the vast population of long-lived dwarfs that add mass without adding metals on short timescales. That standard initial mass function sets the baseline expectation for how quickly oxygen should accumulate in a typical galaxy, and it is one reason the intuition about billion-year timescales developed in the first place. In the early universe, the initial mass function might have been different. Several theoretical arguments suggest that the first stars were biased toward higher masses. The primordial gas was metal-free, which means it could not cool as efficiently as modern molecular clouds that use carbon and oxygen lines to radiate energy. Less efficient cooling means higher temperatures in collapsing gas clouds. Higher temperatures mean higher Jeans masses, which is the minimum mass at which a gas cloud becomes gravitationally unstable and can collapse. A higher Jeans mass means that the typical star forming from primordial gas is more massive than stars forming today. If early star formation produced a top-heavy initial mass function, the enrichment timeline compresses dramatically. Massive stars of 100 solar masses or more can synthesize and eject large quantities of oxygen in just a few million years. A burst of such stars could enrich a small galaxy's gas significantly in timescales that are short even by the standards of the cosmic dawn. The key question is how top-heavy the first stellar generations actually were, and that question cannot be answered from theory alone because the simulations that address it are sensitive to assumptions about cooling rates, radiation feedback, and the magnetic field environment of the early universe. Observations of metal-poor stars in the Milky Way halo offer indirect evidence. Those stars are relics from early epochs, and their chemical compositions record what the enriching supernovae produced. The abundance patterns in the most metal-poor halo stars are consistent with enrichment by a population of moderately massive to very massive stars, suggesting that early star formation was indeed biased toward higher masses. But the interpretation is not definitive because those stars probe the chemical history of our own galaxy's early environment, which may not be representative of the more extreme high redshift systems where the oxygen claim is being made. Population III stars, the hypothetical first stellar generation formed from purely primordial gas, are the most extreme case of this reasoning. If they were very massive, potentially hundreds or even thousands of solar masses, they could have had lifetimes of only 1,000,000 years or less and could have synthesized substantial oxygen before dying. Their deaths would have been violent, producing powerful supernovae or even parainstability supernovae for the most massive cases. Parainstability supernovae completely disrupt the star and eject all synthesized material into the surrounding gas without leaving behind a compact remnant. The oxygen yield per event is enormous, and a relatively small number of such explosions could enrich a compact early galaxy's gas to detectable levels. The problem with relying heavily on population III stars to explain early oxygen is that we have not directly observed them, and their properties are therefore theoretically uncertain. We know they must have existed because the universe began with no metals and gradually acquired them. We know their deaths must have contributed to early enrichment because the metals had to come from somewhere. But we do not know how massive they typically were, how many formed per unit gas mass, or how efficiently their ejecta mixed into the surrounding gas. Each of these unknowns can change the predicted oxygen abundance by factors of several, and those factors determine whether the observed level of enrichment is plausible or implausible in the available time. Star formation efficiency adds another dimension to the problem. Even if individual stars produce oxygen quickly, the galaxy needs to convert enough gas into stars to produce a detectable amount of oxygen in the observable emission. Star formation efficiency is the fraction of available gas that actually forms stars, and in modern galaxies it is typically a few percent per dynamical time, meaning only a small fraction of the gas converts to stars in each orbital period. If early galaxies were similarly inefficient, they would form fewer stars and produce less oxygen per unit time, extending the enrichment timeline. If they were more efficient, the enrichment would proceed faster. Theoretical models and simulations suggest that early star formation efficiency can vary by large factors depending on the halo mass, the gas density, and the feedback environment. In the most massive and dense early halos, the gas can be compressed to very high densities where star formation is rapid and efficient. In these conditions, a galaxy can convert a large fraction of its gas into stars in a single burst, producing a correspondingly large amount of oxygen in a short time. The galaxy we are considering might be exactly this kind of system, caught in the act of an intense burst that produces strong emission lines, even though the underlying stellar mass is still modest. Feedback is the counterweight to efficient star formation. When massive stars form and begin producing ionizing radiation and eventually explode as supernovae, they inject energy into the surrounding gas. That energy can heat the gas, drive outflows, and disrupt the conditions needed for continued star formation. Feedback is therefore self-limiting in a way that constrains how much star formation can occur in a short burst. In shallow gravitational potential wells, which describe early low-mass halos, feedback can be especially disruptive because the binding energy of the gas is low. A single energetic supernova can unbind a significant fraction of the gas in a small early halo, temporarily quenching star formation and metal retention. The tension between efficient star formation and disruptive feedback is one of the central unresolved problems in early galaxy formation. Simulations capture this tension, but resolve it differently depending on how feedback is modeled. Subgrid prescriptions for feedback can range from very strong, where a few supernovae essentially remove all the gas from small halos, to relatively weak, where the gas is disturbed but not ejected. The choice among these prescriptions has a large effect on the predicted chemical enrichment of early galaxies, and current observations are not precise enough to definitively discriminate between them. One way to partially circumvent this tension is through the concept of rapid recycling. In a dense early galaxy, gas ejected by one round of supernovae might cool quickly and fall back into the star-forming region on timescales much shorter than the dynamical time of a larger modern galaxy. This rapid recycling means that the effective star formation efficiency, integrated over multiple generations, can be much higher than the efficiency in any single episode. The galaxy essentially recycles its gas repeatedly, processing it through multiple generations of stars before the metals are finally locked into long-lived low-mass stars or expelled permanently into the intergalactic medium. Rapid recycling is plausible in dense high-redshift environments where the cooling time is short and the gravitational well, while shallow, still holds much of the ejected material within a limited radius. It is also consistent with some observational evidence from lower redshift analogs, compact star-forming galaxies at redshifts of 2 to 4 that show chemical enrichment patterns suggesting efficient recycling of stellar ejecta. Whether those analogs are appropriate proxies for the even more extreme conditions at Z around 14 is uncertain, but they provide at least a plausibility argument that rapid enrichment is not physically impossible. The escape fraction of metal-enriched gas is the other critical variable. Supernovae not only heat gas, they drive it outward in winds that can carry metals far from the star-forming region. If those metals escape the halo entirely and enter the intergalactic medium, they are not available to contribute to the observed emission lines of the galaxy. They are lost from the system, at least temporarily. Early galaxies with shallow potential wells lose metals more easily than later massive galaxies, which means their effective enrichment is lower than their total metal production would suggest. This effect works against the detectability of oxygen in early galaxies because the metals that are produced tend to leave. However, if the star formation is sufficiently intense and concentrated, the enriched gas may not escape immediately. The outflow takes time to accelerate, and the emission lines are produced in the phase before the wind has carried the metals away. We might be observing a galaxy at the moment of peak emission, when the star formation is at its most intense and the metals have not yet been expelled. In this scenario, the oxygen detection is real but transient, a snapshot of a brief phase rather than evidence of sustained chemical maturity. The galaxy would look chemically evolved in this moment, but would become much more metal-poor in its observable signatures once the outflow carries the enriched gas away. This scenario has a specific prediction. The galaxy should show signs of powerful outflows in addition to strong emission lines. Outflow signatures include broad wings on emission line profiles, where the high-velocity gas produces line emission shifted to large velocity offsets from the systemic redshift. At Z around 14, these broad wings would be extremely difficult to detect because they require high spectral resolution and high signal-to-noise ratios that are challenging even for Webb. But if future observations can detect them, the scenario of transient enrichment becomes more quantitatively testable. The mass of the dark matter halo hosting the galaxy is another constraint that interacts with all these processes. More massive halos have deeper potential wells that retain more gas and metals, support more sustained star formation, and are more likely to have accumulated enough gas to produce a detectable starburst. The mass function of halos at Z around 14 in lambda CDM is steep, meaning massive halos are exponentially rarer than low-mass halos at this early epoch. A galaxy in a massive halo at Z equals 14. 32 would be an extreme outlier by that standard, a rare peak in a steeply falling distribution. Being an outlier is not impossible. It is expected that some halos will be rare peaks, and that the first such halos to be discovered will be the most extreme ones because they are the brightest. But the abundance of extreme halos at high redshift is itself a test of the cosmological model. Lambda CDM predicts a specific number of halos above a given mass threshold at each redshift, and that prediction depends on the growth rate of structure, and therefore on the cosmological parameters. If the observed number of very luminous early galaxies exceeds the lambda CDM prediction significantly, it suggests either that the halos are more common than expected, which would require a change in the cosmological parameters, or that the galaxies within those halos are more luminous than expected per unit mass, which would require a change in the astrophysical recipes for star formation and feedback. Several recent analyses have suggested that the number of bright early galaxies found by Webb is higher than pre-Webb lambda CDM predictions. This excess, if confirmed, is one of the early surprises of the Webb era. It could be explained by a top-heavy initial mass function that produces more ultraviolet light per unit stellar mass, making galaxies brighter without requiring more mass. It could also be explained by bursty star formation that temporarily boosts luminosity above the time-averaged value, producing a population of momentarily very bright objects that are caught in their luminous phase. Or it could point to genuinely more massive early halos than lambda CDM predicts, which would be a more fundamental challenge to the standard model. Distinguishing among these explanations requires measurements that go beyond photometry and even beyond simple spectroscopy. Stellar mass estimates, which can be derived from the rest frame infrared emission that traces the bulk of the stellar population rather than just the young massive stars, are needed to separate brightness from mass. Dynamical mass estimates, which can be derived from the widths and profiles of emission lines that reflect the velocity dispersion of the gas, are needed to constrain the depth of the potential well. And number counts, which require careful analysis of survey completeness, are needed to establish whether the excess of bright objects is statistically robust. Each of these measurements is challenging at Z around 14. Stellar mass estimates require photometry at wavelengths that correspond to rest frame infrared, which at Z around 14 is shifted to the far infrared and submillimeter, beyond even Webb sensitivity. Dynamical mass estimates require spectral resolution and signal-to-noise ratios that are at the edge of what is currently achievable. Number counts require a survey that is large enough to beat down cosmic variance, which at extreme redshifts requires mosaic observations covering many independent lines of sight. The data that would settle these questions are still being collected and analyzed. In the meantime, the physical picture that emerges from the existing arguments can be summarized as follows. A galaxy producing detectable oxygen at Z around 14 is not impossible within the known laws of physics and within the framework of lambda CDM, but it requires a set of conditions that are at the extreme end of the plausible range. Those conditions include a very massive host halo for this epoch, a top-heavy initial mass function, or extremely high star formation efficiency, minimal loss of enriched gas through early winds, and detection at the precise moment of peak emission when the starburst is most intense and the lines are strongest. The probability that all these conditions are simultaneously satisfied is not zero, but it is not high either. Whether that probability is high enough to make such galaxies as common as the claimed detections suggest is the question that the community is working to answer. The oxygen claim, therefore, does not simply assert that physics is broken. It asserts that the early universe was more extreme than our baseline models predict. That assertion might be correct, and if it is, it points to specific physical ingredients that need to be modified or added in our descriptions of early galaxy formation. Those modifications would not overturn lambda CDM's cosmological framework, but would substantially revise the astrophysical picture of how the first galaxies grew and enriched their gas. The distinction between a cosmological problem and an astrophysical problem is important because the solutions are different, and so are the implications for other areas of physics. A cosmological problem would require changing the expansion history or the growth rate of structure, which would have broad consequences for everything from the CMB to gravitational lensing to the abundance of galaxy clusters. An astrophysical problem would require revising stellar physics, feedback prescriptions, and star formation models, which would affect the predicted properties of early galaxies but would leave the large-scale cosmological framework intact. The oxygen claim, if confirmed, is more naturally an astrophysical problem than a cosmological one, but it cannot be definitively classified without better data on both the galaxy's properties and the broader population of early systems. The hunt for that better data is underway on multiple fronts. Webb continues to survey the early universe with increasing depth and coverage. Ground-based telescopes with adaptive optics can provide complementary high-resolution imaging of strongly lensed high-redshift sources. The Atacama Large Millimeter Array can detect far-infrared continuum and line emission from early galaxies, probing dust and molecular gas content that Webb cannot access. And the planning for the next generation of space observatories is already incorporating the lessons of Webb's early surprises, designing missions that can follow up on the most puzzling results with even greater sensitivity and wavelength coverage. The oxygen at Z around 14 is therefore not just a result. It is a pointer. It points towards specific questions that the next decade of observations must answer. Are bright early galaxies common or rare? Do they show consistent evidence of chemical enrichment, or do only a few extreme cases? Are their host halos consistent with lambda CDM's mass function predictions? And does the pattern of emission lines across a population of early objects tell a consistent physical story, or reveal internal contradictions that suggest systematic errors in the analysis? those questions will not be answered by any single observation or any single paper. They will be answered by the accumulation of data from many sources, analyzed with many methods, and scrutinized by a community that has learned to be both ambitious and skeptical in equal measure. The measurement chain has been examined, and the physical plausibility has been assessed. Now the story must engage more directly with the cosmological framework that gives the oxygen claim its dramatic character. The lambda CDM model does not merely provide a number for the age of the universe at z equals 1432. It provides a complete narrative of how the universe arrived at that point and what it should contain. That narrative is built on a set of observations that constrain the parameters, and those constraints have their own uncertainties and their own tensions. The Hubble constant is the expansion rate of the universe today, and it is the parameter that most directly converts a redshift into a physical distance and a look-back time. Its value has been measured by multiple methods, and those methods disagree. The early universe method uses the CMB to infer the expansion rate, and it arrives at a value of around 67 to 68 kilometers per second per megaparsec. The late universe methods use distance ladders anchored by Cepheid variable stars and calibrated against type Ia supernovae, and they arrive at values closer to 73 kilometers per second per megaparsec. That discrepancy of roughly 8% sounds small, but it is far larger than the stated measurement uncertainties from either method. When two precise measurements of the same quantity disagree by more than their combined uncertainties, the scientific community says they are in tension. The Hubble tension has persisted for years through multiple rounds of improved measurements and expanded data sets. It has not gone away as data quality improved. In fact, the tension has grown in statistical significance as the error bars on both sides have shrunk. Tension that grows when measurement precision improves is one that is unlikely to simply vanish with a small systematic correction. If the Hubble constant is truly higher than the CMB-based estimate suggests, then the universe is slightly younger than lambda CDM currently predicts. At low redshifts, this difference is small, but at extreme redshifts, it compounds. A universe that is expanding faster in the recent past would have had less time to build the structures we observe at high redshift. That sounds like it would make the oxygen problem worse, as there would be even less time to form enriched galaxies. But the relationship between the Hubble constant and the age at a given redshift is more complex because the early universe's expansion rate is dominated by matter and radiation, not by dark energy, which is what the Hubble constant primarily characterizes in the late universe. The full mapping from Hubble constant to early universe age requires specifying the complete expansion history, including the density of radiation, matter, and dark energy at each epoch. If the tension is resolved by changing the dark energy behavior, or by adding new physics that was active in the early universe, the impact on the age at z equals 14 can vary from negligible to substantial depending on the specific model. Some proposed solutions to the Hubble tension, like early dark energy models that temporarily increase the expansion rate in the period just before recombination, do change the relationship between redshift and age at high z in those models. The age of the universe at z equals 14 can be somewhat different from the standard lambda CDM prediction. Early dark energy is a class of models where an additional component with equation of state near -1 becomes important around the time of recombination and then fades away. By temporarily speeding up expansion near that epoch, it changes the acoustic scale of the CMB oscillations and can bring the CMB-inferred Hubble constant into better agreement with the local measurements. But it also changes the growth rate of structure and the mapping between redshift and age in ways that affect predictions for early galaxies. Whether those changes help or hurt the case for oxygen at z equals 14 depends on the specific parameters of the early dark energy model. Interacting dark matter and dark energy models represent another class of solutions to the Hubble tension that can also affect early structure growth. If dark matter and dark energy exchange energy in specific ways, the growth of density perturbations can be modified, changing the predicted abundance of early halos. Some versions of these models can increase the number of massive early halos relative to standard lambda CDM, which would make it easier to accommodate very luminous early galaxies. However, these models must also preserve the CMB's acoustic peak pattern and the baryon acoustic oscillation measurements that constrain the expansion history, limiting how drastically they can modify structure growth. Modified gravity theories offer yet another angle on the problem. If the law of gravity differs from general relativity on cosmological scales, the growth rate of structure can be enhanced or suppressed relative to the standard prediction. Some modifications that increase structure growth at early times could produce more massive halos earlier, providing more hospitable environments for rapid star formation and chemical enrichment. But modified gravity on cosmological scales is heavily constrained by gravitational wave observations, the detailed structure of the CMB, and the consistency of gravitational lensing measurements, which limits the range of modifications that are currently viable. Warm dark matter or fuzzy dark matter, where the dark matter particle has properties that suppress small-scale structure, would go in the opposite direction. These models reduce the abundance of small halos relative to cold dark matter, making it harder to form the very first galaxies. They are therefore not natural solutions to the early enrichment problem and would make it even harder to explain oxygen at z=14. However, they are motivated by potential problems at small scales in the local universe, where the number of small satellite galaxies and the density of halo cores may be lower than pure cold dark matter predicts. The tension between early galaxy observations and small-scale structure observations is one of the active research areas in cosmology. None of these alternative frameworks has achieved the status of a strong competitor to lambda CDM. They are proposed solutions to specific tensions rather than comprehensive alternatives with comparable predictive power across the full range of cosmological observables. Lambda CDM, despite its tensions, remains the model that best fits the largest number of independent data sets simultaneously. The Hubble tension and the early galaxy surprises are stress points, not fractures, at least by current evidence. But stress points that persist through improved measurements are worth tracking carefully because they may eventually become fractures if they fail to resolve. The cosmic microwave background itself carries information about the very early universe that constrains inflation, the hypothetical period of rapid expansion that set the initial conditions for everything that followed. Inflationary models predict a nearly scale-invariant spectrum of primordial density fluctuations, and the measured CMB spectrum is consistent with this prediction. The slight deviation from perfect scale invariance, characterized by the spectral index, is measured to be close to but slightly less than 1, which is what simple inflationary models predict. More exotic inflationary models that produce a significantly different spectral index would change the relative abundance of small and large structures at early times, potentially modifying the early galaxy population. If inflation produced more power on small scales than the simplest models predict, there would be more small-scale density fluctuations, and those fluctuations would collapse into more early halos of small mass. More early halos of small mass means more sites for early star formation, which means more opportunity for early chemical enrichment. The oxygen at z=14 could then be a reflection of inflation rather than of unusual astrophysics within the standard cosmological framework. Testing this idea requires measurements of the CMB on very small angular scales, where the primordial spectrum could differ from scale invariant, but those small scales are partly obscured by secondary effects like the Sunyaev-Zeldovich effect from galaxy clusters and lensing of the CMB by large-scale structure. The baryon acoustic oscillation signature in galaxy surveys provides another angle on the expansion history and structure growth. Surveys like the Dark Energy Spectroscopic Instrument are measuring the distribution of galaxies across cosmic time with unprecedented precision. Those measurements will tighten constraints on dark energy's properties and on the expansion history in ways that will inform whether models like early dark energy are viable solutions to the Hubble tension. They will also improve constraints on structure growth that are relevant to the question of early galaxy abundance. As those data accumulate over the coming years, the observational landscape that the oxygen claim must be consistent with will become more precisely defined. Gravitational lensing surveys, particularly weak lensing surveys like those being conducted by the Euclid satellite and the Rubin Observatory's legacy survey of space and time, will measure the distribution of matter as a function of redshift through the coherent distortions of background galaxy shapes. These measurements probe structure growth in a way that is complementary to galaxy surveys and that is sensitive to the combination of matter density and structure growth rate. Discrepancies between weak lensing measurements and CMB-based predictions have been reported in previous surveys, suggesting that structure growth at late times might be slightly suppressed relative to the standard expectation. If that suppression is real, it could indicate that the growth rate of structure is somewhat lower than lambda CDM predicts, which would be relevant to interpreting the abundance of early massive halos. The interaction between all these observations is what gives cosmology its power and its complexity. No single measurement settles any question definitively. Each measurement constrains a combination of parameters, and the full parameter space is only pinned down by combining many measurements that each break different degeneracies. The oxygen claim at Z equals 14 is one data point in this larger picture. It is a provocative data point because it sits at the edge of the universe and appears to show chemistry that challenges naive expectations. But it is not yet a sufficiently well-characterized data point to decisively change any cosmological parameter or to definitively require new physics. What it does is sharpen the questions. It forces us to be more precise about what we mean when we say early galaxy formation is well understood. It reveals that some of our most basic assumptions about the timescales of chemical enrichment may be too conservative, and it motivates both the observational work needed to confirm or revise the measurement and the theoretical work needed to test whether our astrophysical models can accommodate rapid early enrichment within the existing cosmological framework. The next generation of observations will either confirm the oxygen detection and build it into a population of similar objects that demand a comprehensive explanation, or they will reveal systematic errors that resolve the puzzle more mundanely. Either outcome will advance understanding. Either outcome will teach the community something it did not know about how the earliest galaxies formed and how the universe built its first chemistry from the pristine hydrogen and helium that the Big Bang produced. And in that teaching, the mystery of the impossible galaxy will serve its highest scientific purpose as a probe of assumptions rather than a claim of certainty. The physical arguments have been laid out, and the cosmological framework has been stress-tested. Now the story must turn to what the broader population of early Webb discoveries reveals, because the oxygen claim does not exist in isolation. It sits inside a rapidly growing catalog of surprising early objects, each one carrying its own set of tensions with pre-Webb expectations. Understanding that catalog is essential for judging whether the oxygen galaxy is an isolated anomaly or part of a pattern that demands a systematic explanation. Before Webb launched, the theoretical community had a reasonably confident picture of what the telescope would find at extreme redshifts. That picture was built on extrapolations of the luminosity function, the statistical distribution of galaxy brightnesses, from lower redshifts where data were plentiful. The luminosity function describes how many galaxies exist per unit volume above a given luminosity threshold, and it has a characteristic shape that falls steeply at the bright end. At high redshifts, the bright end was expected to fall even more steeply because massive galaxies were supposed to be rare and still assembling in the hierarchical framework. The pre-Webb predictions were not made carelessly. They were grounded in simulations that had been calibrated against observations of galaxies at redshifts of 2, 3, and 4, where data were abundant and models had been refined over decades. Those simulations captured the essential physics of galaxy formation, including gas cooling, star formation, feedback from supernovae and active galactic nuclei, and the growth of dark matter halos through mergers and accretion. The predictions were the best available synthesis of everything the community understood about how galaxies grow. Webb's first deep fields revealed something different. The number of bright galaxy candidates at redshifts above 8, 9, and 10 was larger than many pre-launch predictions, not by a factor of a few, which could be explained by modest adjustments to feedback or star formation efficiency, but by factors that in some analyses approached an order of magnitude at the brightest luminosities. The excess was concentrated at the bright end of the luminosity function, exactly where the predictions were most confident about a steep decline. The bright end was not just higher than expected, it was shaped differently, with a shallower slope that implied a population of very luminous early galaxies that the models had not anticipated. The initial reaction from the community was appropriately cautious. Photometric redshifts at these distances are uncertain, and the early analyses were performed quickly on data that had not been fully characterized in terms of calibration and systematic errors. Several high-profile candidates from the first year of Webb observations were subsequently revised to lower redshifts when spectroscopic follow-up was obtained. Those revisions were widely reported, and they correctly calibrated public and scientific expectations that the most extreme claims should be treated as preliminary until spectroscopic confirmation arrives. But after accounting for those revisions, a residual excess remained. The galaxies that survived spectroscopic scrutiny at high redshifts were still more luminous than the pre-launch predictions suggested they should be. The excess was smaller than the raw photometric samples implied, because many of the most extreme candidates turned out to be at lower redshifts, but it was not zero. Something about early galaxies was producing more ultraviolet light per unit volume than the models expected, and that excess demanded an explanation. Several explanations have been proposed, and they differ in how deeply they challenge the existing framework. the least disruptive explanation is that the dust content of very early galaxies is lower than assumed in the models. When astronomers extrapolate the luminosity function from lower redshifts, they apply corrections for dust attenuation, which dims galaxies by absorbing ultraviolet light and re-emitting it at longer infrared wavelengths. Those corrections are calibrated on galaxies at redshifts of 1 to 3, where dust content has been measured directly. If early galaxies at redshift 8 and above have less dust, the intrinsic luminosity is higher than the attenuation-corrected luminosity from lower redshift calibrations would suggest. A population of less dusty early galaxies would appear brighter in the ultraviolet and would therefore inflate the apparent luminosity function relative to dust-corrected predictions. This explanation is physically motivated because dust grains are made from metals, and metal-poor early galaxies should have less dust. It is also observationally testable because ALMA can detect thermal dust emission in galaxies at high redshift, and the non-detection of dust emission in some early Webb candidates is consistent with low dust content. However, the correction for dust attenuation at these redshifts is uncertain enough that it cannot definitively explain the full magnitude of the excess, and some observed galaxies appear bright enough that even zero dust would not fully account for their luminosity within standard star formation models. A more disruptive explanation involves the initial mass function. If early galaxies formed more massive stars per unit stellar mass than later galaxies, they would produce more ionizing ultraviolet photons and would appear more luminous per unit stellar mass assembled. A top-heavy initial mass function, where the distribution of stellar masses is shifted toward higher values, could explain the brightness excess without requiring more star formation in absolute terms. The galaxies would contain less total stellar mass than their luminosity implies under the standard initial mass function assumption, which would actually make them easier to accommodate within lambda CDM's halo mass predictions. This explanation has the advantage of connecting to the arguments about rapid chemical enrichment discussed earlier. If the initial mass function is top-heavy, enrichment is fast and luminosity is high, potentially explaining both the brightness excess and the oxygen detection with a single physical modification. The challenge is that a strongly top-heavy initial mass function would also change the ratio of different types of supernovae, the production of specific chemical elements, and the long-term chemical evolution of galaxies. Those consequences can be tested against observations of chemical abundances at lower redshifts, where data are more detailed and numerous. Bursty star formation is a third explanation that has gained considerable traction. In this picture, early galaxies do not form stars at a steady rate, but rather in violent bursts separated by quiescent intervals. During the burst, the galaxy is enormously luminous, far above the luminosity expected from its time-averaged star formation rate. During the quiescent interval, the galaxy is dim and might not be detected at all. If surveys catch many galaxies in their burst phase, the observed luminosity distribution will appear to have more bright objects than a model based on steady star formation would predict, even if the total stellar mass assembled is consistent with lambda CDM expectations. Bursty star formation is not just an ad hoc explanation. It is a natural consequence of the same feedback processes that regulate star formation in small halos. When a burst of star formation injects energy into the gas through supernovae and stellar winds, the gas is heated and expelled, quenching the star formation. After some time, the gas cools and falls back, triggering the next burst. This cycle has been seen in simulations of early dwarf galaxies, and it produces galaxies that vary in luminosity by large factors over timescales of tens to hundreds of millions of years. At high redshift, where the dynamical timescales are shorter, the burst and quench cycles can be rapid enough that survey observations frequently catch galaxies in luminous phases. The bursty star formation explanation has a specific prediction. The scatter in the relationship between galaxy luminosity and underlying halo mass should be large at high redshift, and it should decrease at lower redshifts as galaxies grow more massive and their star formation becomes more steady. That prediction can be tested by comparing the scatter and luminosity functions across different redshifts and by looking for evidence of galaxies that appear to be in quiescent intervals between bursts. Some early Webb observations have indeed found what appear to be passive or low star formation galaxies at high redshifts, which would be consistent with the quiescent phase of a bursty cycle. The most disruptive explanation for the brightness excess is a genuine revision to lambda CDM structure growth predictions. If the abundance of massive dark matter halos at high redshift is actually higher than the standard model predicts, then there are simply more environments capable of hosting luminous early galaxies. This would require changing the growth rate of structure, which in turn would require changing the cosmological parameters, the nature of dark matter, or the initial conditions from inflation. As discussed in the previous section, such changes must be consistent with CMB observations and other cosmological probes, which severely limits the allowed range of modifications. Some researchers have pointed out that the current constraints on structure growth at high redshift are not as tight as the constraints at low redshift, simply because fewer observations probe the early universe directly. There may be more room in the high redshift growth rate than the low redshift extrapolation suggests. If inflation produced somewhat more small-scale power than the simplest models predict, or if the dark matter had properties that enhanced early clustering, the halo mass function at high redshift could be higher than standard predictions. Detecting this difference requires precisely measuring the abundance of early massive halos, which is an ongoing observational challenge. The brightness excess debate has direct implications for the oxygen claim. If early galaxies are genuinely more luminous per unit stellar mass than expected, then the star formation rates inferred from their luminosity are overestimated. That means less total stellar mass has actually been assembled, and less total metal production has occurred than the luminosity implies. In this scenario, the oxygen detection becomes harder to explain because the galaxy has actually processed less gas through stars than its brightness suggests. Paradoxically, the explanation that makes early galaxies easier to accommodate in lambda CDM's halo mass budget also makes the chemical enrichment harder to explain. Conversely, if the brightness excess is due to bursty star formation, then the galaxy during the burst has converted a large fraction of its gas into stars very rapidly. That rapid conversion produces a lot of metals in a short time, potentially explaining the oxygen detection. The burst scenario, therefore, has the nice property of connecting the brightness excess to the chemical enrichment, making both observations symptoms of the same underlying physics. That internal consistency is attractive, even if the individual elements of the explanation are not yet fully tested. The population context also matters for understanding how typical or atypical the oxygen galaxy is. If many galaxies at Z around 14 show similar emission line properties, the detection is not an extreme outlier, but reflects something generic about early galaxy formation. If it is isolated, it might represent a genuinely rare extreme event, a massive burst in an unusually massive halo, that was detected only because it happened to be bright enough to be observable. Both possibilities are scientifically interesting, but they call for different explanations and different follow-up strategies. Current data cannot decisively answer the typicality question because the sample of spectroscopically confirmed galaxies at Z above 12 remains small. Every confirmed high redshift galaxy required substantial telescope time to characterize, and the demand for that time greatly exceeds the supply. The selection effects in the existing sample are complex, favoring galaxies with strong emission lines and high ultraviolet luminosities, which are precisely the galaxies that might appear more chemically mature than average. A fair census of early galaxy chemistry would require observing a complete sample defined by some physical criterion like stellar mass or host halo mass, not by emission line strength. That kind of complete census is not yet achievable, but it is a goal that future surveys are working toward. The galaxy overdensities found by Webb in some deep fields add another dimension. Early galaxies are not randomly distributed. They trace the underlying dark matter distribution and tend to cluster in the dense nodes of the cosmic web. If a galaxy at Z around 14 sits in a protocluster environment, surrounded by other galaxies at similar redshifts, its star formation history could have been accelerated by the enhanced gas supply and merger rate in that dense environment. Protoclusters are environments where galaxies can grow faster and enrich more quickly than isolated galaxies because the available gas is more abundant and the merger-driven starbursts are more frequent. Detecting protocluster environments at extreme redshifts requires finding multiple galaxies within a small angular region of the sky at the same redshift. Webb has found several examples of such structures at redshifts between 8 and 12, where 2 or more galaxies appear to be physically associated. Extending that search to Z around 14 would require both finding multiple candidates at that redshift and confirming the association spectroscopically, which is an enormous observational challenge given the faintness of individual sources. But if the oxygen galaxy is embedded in an early protocluster, its unusual chemistry would be less surprising because the environment would accelerate all the processes needed for early enrichment. The analogy with lower redshift protoclusters is instructive. In the local universe and at intermediate redshifts, galaxy clusters show accelerated evolution compared to field galaxies. Cluster galaxies tend to be older, more massive, and more metal-rich than field galaxies of the same stellar mass. The cluster environment accelerates star formation at early times and then quenches it through ram pressure stripping and other mechanisms, leaving behind an old, passive population by the time the cluster is fully assembled. If protoclusters at Z around 14 show similarly accelerated evolution, their member galaxies could appear chemically mature at an epoch when field galaxies are still in their infancy. This environmental explanation does not require any modification to lambda CDM's cosmological parameters or to stellar physics. It requires only that the variance in galaxy formation histories is large enough to allow the dense cluster environments to produce chemically mature systems, while the field remains chemically primitive. Lambda CDM does predict large variance in galaxy formation histories as a natural consequence of the variance in halo assembly times, and protocluster environments naturally assemble earlier in the hierarchy because their large-scale overdensity provides extra gravitational pull that accelerates collapse. The environmental scenario is testable with current and future facilities. If the oxygen galaxy is part of a protocluster, there should be other galaxies at the same redshift within a projected radius of a few arcminutes. Those companion galaxies might be detectable with very deep Webb imaging, even if they are too faint for spectroscopy. The angular power spectrum of galaxy positions at high redshift, which measures the clustering of early objects, can reveal whether they are more strongly clustered than random, as would be expected if they prefer dense environments. And future submillimeter surveys can detect the far-infrared continuum from dust emission in cluster galaxies, providing an independent tracer of the early mass distribution. The broader lesson from the brightness excess debate and from the environmental considerations is that the early universe was likely more complex and more varied than our baseline models anticipated. The models were built on averages and on the dominant physical processes at later times, and they may have systematically underestimated the tails of the distribution. First galaxies that we detect are by construction the most extreme ones, the brightest, the most massive, the most chemically enriched. They represent the high end of a distribution whose mean and variance are not yet well characterized. Drawing conclusions about the typical early galaxy from the detected extreme population is a sampling problem as much as a physics problem. Webb is beginning to address that sampling problem by providing the deepest views of the sky ever achieved in the infrared. The faintest objects in the Webb deep fields are pushing toward the characteristic luminosity of the early galaxy population, the luminosity at which the number density of galaxies begins to fall steeply. As the survey area and depth increase, the statistical characterization of the early galaxy population will improve, and it will become possible to separate the extreme outliers from the typical objects with increasing confidence. That statistical foundation is essential for turning individual detections, like the oxygen galaxy, into statements about the physics of early galaxy formation. The interplay between individual discoveries and population statistics is one of the defining characteristics of modern observational cosmology. The era of single-object discoveries that define a field is giving way to an era of large samples, where the signal emerges from statistics rather than from any individual measurement. The oxygen claim is an example of the former mode, a single object making a provocative statement. Whether that statement represents real physics will ultimately be decided by the latter mode, through the accumulation of consistent evidence from many objects characterized with increasing precision. The transition from individual discovery to statistical confirmation is often the most scientifically productive phase of any research program, and that transition is currently underway for the study of the earliest galaxies. The oxygen galaxy sits at the frontier of that transition. It is a flag planted at an extreme point, marking the edge of what is currently observable and raising questions that point toward the next generation of measurements. Whether the flag marks a genuine discovery or a false summit will become clear as the investigation deepens and widens. In the meantime, it serves the essential function of organizing the community's attention, directing telescope time toward the most pressing questions, and motivating the theoretical and computational work needed to interpret what will eventually be a much richer observational data set. Having examined the population context, the story must now turn to the specific physical mechanisms that could produce detectable oxygen in the observed timeframe. Theoretical case needs to be built carefully, because the question is not simply whether oxygen can form, but whether the complete chain of events from pristine gas to detectable emission can plausibly occur within the available time. That chain is long and each link has its own constraints. The starting point is the gas supply available to the first galaxies. In lambda CDM, the first halos to collapse are the smallest ones, forming from the earliest overdensities in the primordial density field. These small halos gradually grow through mergers and accretion, assembling the larger systems in which more substantial galaxies can form. At z equals 14, the most massive halos are still relatively small by later standards, perhaps tens of billions of solar masses in total mass including dark matter. The baryonic mass available for star formation is roughly 1/6 of that, corresponding to the cosmic baryon fraction, giving a raw material supply of perhaps a few billion solar masses. That supply is not all available simultaneously. Gas falls into halos on timescales set by the halo's dynamical time, which at high redshift is short compared to later epochs. But the gas must also cool before it can form stars, and cooling depends on the gas density and the presence of coolants like molecular hydrogen and later metals. In pristine conditions, molecular hydrogen is the primary coolant, but it is fragile and easily dissociated by ultraviolet radiation from the first stars. The competition between molecular hydrogen formation and destruction is one of the critical bottlenecks in early star formation, and its outcome determines whether the first halos can efficiently convert their gas into stars. If molecular hydrogen cooling is efficient in the densest early halos, gas can cool rapidly and fragment into stars. The first burst of star formation can then occur within a few tens of millions of years of the halo, reaching the threshold mass for gas accretion. In that burst, the most massive stars can form, evolve, and explode within a few million years, producing the first generation of metals. The metals then contribute to line cooling, making subsequent star formation even more efficient as the gas can now cool to lower temperatures and form stars across a wider range of densities. This positive feedback loop, sometimes called metal cooling runaway, is one mechanism by which early galaxies could rapidly transition from chemically primitive to chemically enriched. The runaway is not guaranteed, however. Feedback from the first stars and supernovae can disrupt the gas before the loop can establish itself. The ultraviolet radiation from massive stars photodissociates molecular hydrogen, removing the primary coolant and heating the gas. Supernovae inject kinetic energy that can drive the gas out of the halo. If the feedback is strong enough, it can interrupt the star formation after only a small fraction of the available gas has been converted, leaving most of the gas in a hot, metal-poor state that is inhospitable to further star formation until it cools again. The outcome of this competition depends sensitively on the ratio of the halo's gravitational binding energy to the energy injected by feedback. In small halos, the binding energy is low and feedback tends to win, suppressing star formation. In large halos, the binding energy is high and the gas can be stirred without being permanently expelled. The transition between these regimes, sometimes characterized by a critical halo mass or circular velocity, determines which early halos can sustain star formation through multiple generations and which ones are effectively shut down after a single burst. For the oxygen claimed to be explained by early star formation within a single halo, the halo must be above this critical mass threshold at the time of observation. If it is, the halo can retain enough of the supernova ejecta to enrich subsequent generations of stars, and the oxygen abundance can build up over multiple rapid cycles. If it is below the threshold, the oxygen from the first burst is expelled into the intergalactic medium, and the observable galaxy remains chemically primitive despite having produced substantial metals. The critical mass threshold is itself uncertain because it depends on the feedback prescription, the gas accretion rate, and the radiation environment. In a universe where reionization has already started to heat the intergalactic medium, even relatively massive halos can struggle to accrete fresh gas because the infalling gas is warm and has more pressure support. But at z equals 14, reionization is just beginning, and the intergalactic medium is still mostly neutral and cool. In this environment, even moderately massive halos can accrete efficiently, providing the raw material for rapid star formation and enrichment. The concept of metal retention efficiency is important here. Not all the metals produced by supernovae stay within the galaxy. Some are ejected in winds and distributed into the circumgalactic medium or the intergalactic medium. The fraction that remains in the galaxy, available to enrich the next generation of stars and to produce the observable emission lines, is the metal retention efficiency. In small, low-mass halos, this efficiency can be very low, with most metals escaping in energetic winds. In more massive halos with deeper potential wells, the efficiency is higher. For the oxygen emission to be detectable, The metals must not only be produced, but must remain in the galaxy's gas in a physical state that produces emission. The OIII line specifically requires doubly ionized oxygen, which means the gas must be exposed to photons with energies above 35 electron volts. Only very hot stars, specifically those with surface temperatures above about 40,000 Kelvin, produce substantial numbers of such photons. The stellar populations that produce the ionizing photons required to excite detectable OIII emission are young and massive, which means they must have formed recently. The connection between OIII emission and young massive stars is direct and physical, not merely statistical. This connection has an important implication. Detectable OIII emission at Z equals 14 requires both that metals are present and that young massive stars are currently forming and irradiating the gas. If the star formation has ended, the massive stars die quickly and the ionizing radiation fades. Within tens of millions of years of the last burst ending, the OIII emission would drop dramatically even if the oxygen remains in the gas. The detection of strong OIII emission is therefore evidence not only of past enrichment, but of currently ongoing or very recently ended star formation. The galaxy we are observing is caught in an active phase, and the emission lines are the signature of that activity rather than a long-term equilibrium state. This time-limited nature of OIII emission helps explain how oxygen can be detected so early. The key is not that the galaxy has been forming stars continuously for a long time and has accumulated metals gradually. The key is that a recent burst of massive star formation both produced the oxygen and provided the ionizing radiation to make it visible. The burst might be the first burst, or it might be a later burst following an earlier quiescent period. What matters is that the burst is occurring now, from the perspective of the observation, and that the gas being irradiated contains enough oxygen to produce a detectable line. The minimum time required for this scenario is set by the lifetime of the most massive stars, plus the time needed to collect enough gas for a burst. Very massive stars of 100 solar masses or more have main sequence lifetimes of only about 2 to 3 million years. If the first stars of this type formed 2 million years after the halo collapsed and began accreting gas, their deaths would begin producing oxygen at 4 to 5 million years. The supernova ejecta would then mix into the surrounding gas over the next few million years, depending on the mixing efficiency. By 10 to 20 million years after the initial collapse, the gas could in principle contain detectable levels of oxygen, and the subsequent star formation could produce the ionizing radiation needed to excite the OIII line. This back-of-the-envelope estimate suggests that the minimum enrichment time is on the order of 10 to 20 million years. At Z equals 14, the universe is 290 million years old, which is much longer than this minimum. Even if the halo only collapsed and began forming stars 100 million years before the observation, there is ample time for one or more enrichment cycles. The question is not whether the available time is long enough in principle, but whether the physical conditions in early halos are conducive to the rapid and efficient enrichment required. Those physical conditions include sufficiently high gas densities for rapid star formation, a sufficiently deep potential well for metal retention, the presence of strong ionizing radiation from massive stars, and a geometry that allows the ionized oxygen emission to escape without being absorbed by intervening neutral gas. Each of these conditions places requirements on the halo properties and the galaxy's internal structure that must be satisfied simultaneously for the detection to make sense. The gas density requirement is probably satisfied in the earliest massive halos because those halos are forming in regions of the universe that were significantly denser than average. The high redshift means that even typical intergalactic densities are much higher than today, and the overdense regions that seed the first massive halos are denser still. High gas density accelerates all the relevant processes, from molecular hydrogen formation to star formation to supernova-driven mixing of metals. The potential well requirement is more restrictive. As discussed, halos must be above a critical mass to retain metals against supernova feedback. At Z equals 14, a halo of 10 to 100 billion solar masses in total mass would be among the rarest and most massive objects in the universe, sitting at the extreme tail of the halo mass function predicted by lambda CDM. Such a halo would be so rare that finding one in a small survey volume would be statistically unlikely. But survey volumes at extreme redshifts are not small in terms of the number of independent lines of sight that have been sampled, and cosmic variance can produce local overdensities that increase the probability of finding extreme objects in any given observed field. The ionizing radiation requirement is naturally satisfied by the star formation itself. If massive stars are forming, they produce ionizing photons. The relevant question is whether enough of those photons reach the oxygen-containing gas to excite the OII transition. In compact high-redshift galaxies, the gas in the ionizing stars can be physically close, maximizing the ionizing flux experienced by the gas. In extended or clumpy galaxies, some of the gas might be shielded from the ionizing radiation, reducing the OII emission relative to what would be expected from the total oxygen content. The escape of emission line photons through neutral gas is the final constraint. The OII line at 5007 angstroms is not resonantly absorbed by hydrogen in the way that Lyman alpha is, so it does not suffer the same severe damping by intervening neutral gas. However, if the galaxy is surrounded by dense neutral gas at the same redshift, some of the photons might be absorbed by dust associated with that gas. At Z equals 14, dust content should be low given the short time available for metal production, but it is not necessarily zero if the galaxy has already experienced earlier star formation. The transparency of the circumgalactic medium to OII emission is therefore another variable that affects the detectability of the line. When all these physical considerations are combined, the picture that emerges is one of constrained but not impossible early oxygen detection. The scenario requires a combination of physical conditions that are each plausible individually, but are collectively more demanding than the typical case. The required halo mass is at the extreme end of the lambda CDM prediction for that epoch. The required metal retention efficiency is higher than expected in low-mass halos. The required star formation efficiency in the burst must be high, and the observation must catch the galaxy at the specific moment when all conditions are aligned for maximum emission line strength. The probability of all these conditions being simultaneously satisfied is not zero, but it is not high. Whether the claimed detection frequency is consistent with that probability depends on the survey volume, the completeness, and the selection effects, all of which are incompletely characterized for the current sample. The claim is therefore physically possible but statistically constrained. And the statistical constraint is where the most productive next round of observations will focus. To sharpen the physical picture, it is useful to compare with direct simulations of early galaxy formation. The most sophisticated current simulations of the first galaxies combine cosmological dark matter growth with hydrodynamics, radiative transfer, and stellar feedback. These simulations have names like First Light, Fire, Sphinx, and Renaissance, and they have been pushing to higher resolution and more detailed physics over the past decade. Each simulation makes predictions for the early galaxy population that can be compared with Webb's observations. The general finding from these simulations is that early star formation is indeed bursty and variable, consistent with the arguments about feedback-regulated cycles. The simulations also predict that the first galaxies are compact, with high surface densities of star formation, which is consistent with the observed properties of high redshift candidates. However, the simulations have not consistently predicted the full brightness and apparent chemical maturity of the most extreme objects that Webb is finding. The discrepancy between simulations and observations is one of the active debates in the field, and it may reflect limitations in the simulations rather than failures of the underlying cosmological model. Limitations in the simulations include the resolution of the grid or particle distribution, which determines how well the simulations capture the small-scale physics of star formation and feedback. At the resolution typical of cosmological simulations, individual star formation events are not resolved. Instead, prescriptions that relate bulk gas properties to star formation rates are applied at each grid cell or particle. These prescriptions are calibrated on lower redshift observations and may not accurately represent the conditions in the first galaxies. The subgrid prescriptions for supernova feedback are particularly uncertain because they determine how efficiently supernovae drive outflows and how much of the metal-enriched ejecta escapes versus stays within the galaxy. Higher resolution simulations that zoom in on individual early halos can resolve more of this physics, but they are computationally expensive and can only follow a small number of halos for a limited time range. The rare massive halos that might host the oxygen galaxy are particularly difficult to simulate at high resolution because they require both a large enough cosmological volume to find them in the first place and sufficient resolution to model the internal physics. The combination of large volume and high resolution is computationally prohibitive with current hardware. Machine learning approaches are beginning to supplement traditional simulation methods by training on high-resolution small-scale simulations and applying the learned relationships to larger scales. These emulator techniques can potentially bridge the gap between the resolution needed to capture early star formation physics and the volume needed to sample the rare massive halos at extreme redshifts. They are not yet mature enough to replace traditional simulations, but they represent a promising direction for the next generation of theoretical work on early galaxy formation. Analytic models of early chemical enrichment provide a complementary perspective. By tracking the mass flow between gas, stars, and outflows, and by parameterizing the star formation efficiency and metal yields, these models can rapidly explore the range of early galaxy histories that are physically plausible. They are less detailed than simulations, but much faster, allowing systematic exploration of parameter space. The oxygen detection can be used as a constraint on these models, ruling out combinations of parameters that would not produce enough oxygen in the available time, and identifying the combinations that would. The analytic models generally confirm that rapid enrichment to detectable oxygen levels is possible if the star formation efficiency and metal retention are both high. They also reveal that the enrichment history is sensitive to the timing of the first burst relative to the halo formation, to the mass of the halo, and to the effectiveness of molecular hydrogen cooling in the pre-enrichment phase. The uncertainty in these parameters is large enough that a wide range of early enrichment histories is currently consistent with the theoretical framework, which means the oxygen detection cannot yet be used to strongly prefer any particular physical model over the alternatives. The combination of simulation constraints and analytic model exploration provides a theoretical landscape within which the oxygen claim can be evaluated. That landscape has regions where the detection is expected and regions where it is not. The oxygen galaxy appears to sit near the boundary between these regions, close enough to the expected region to be plausible, but far enough to be noteworthy. Whether it is inside or outside the expected region depends on details that are not yet pinned down, which is why the theoretical debate is ongoing even as the observational work continues. The theoretical landscape also reveals that the oxygen detection, if confirmed, is not a single-point constraint. It constrains combinations of parameters simultaneously, and different combinations can produce the same observable. This degeneracy means that the oxygen detection alone cannot identify which physical mechanism is responsible for the rapid enrichment. Additional constraints are needed to break the degeneracy, and those constraints come from other observational diagnostics that are sensitive to different combinations of the underlying physical parameters. For example, the ratio of different emission lines provides constraints on the ionization parameter and the gas temperature that are independent of the oxygen abundance. The line width provides constraints on the gas velocity dispersion and therefore on the dynamical mass of the system. The continuum shape provides constraints on the age and initial mass function of the stellar population. Each of these diagnostics reduces the allowed region in parameter space, and combining them can in principle identify the physical conditions that produce the observed spectrum. The challenge is that at Z around 14, measuring these additional diagnostics with sufficient precision requires telescope time that is not yet available for this specific object. The theoretical foundation has been examined and the observational context has been established. Now the story must confront the question that underlies all the others, not whether the oxygen detection is real and not whether it is physically plausible, but what it means for the cosmic clock that converts redshift into age. The cosmic clock is not an independent entity. It is built into lambda CDM, and it inherits all the assumptions of that framework. When those assumptions are stressed by observations at the edge of the universe, the clock itself comes under scrutiny. The age of the universe at Z equals 14. 32 is approximately 290 million years under the standard lambda CDM parameters. That number comes from integrating the Friedmann equation with the best fit values of the Hubble constant, matter density, and dark energy density from CMB observations. The equation itself follows from general relativity applied to a homogeneous and isotropic universe, assumptions that are well supported on large scales, but may be approximate on the smaller scales relevant to individual galaxies. The age is therefore a precisely stated number built on well-supported but not perfectly certain foundations. The uncertainty in the age at Z equals 14. 32 comes from two sources. The first is parameter uncertainty, meaning the finite precision of the measurements that constrain H0, matter density, and dark energy density. Within the current best-fit parameters and their reported uncertainties, the age at this redshift is determined to a precision of a few percent, perhaps 10 to 20 million years. That range is small enough to matter for the enrichment timeline, but not large enough to fundamentally resolve the tension. Moving the clock by 20 million years does not give a qualitatively different picture of what can happen in the available time. The second source of uncertainty is model uncertainty, meaning the possibility that lambda CDM itself is not the correct description of the universe's expansion history. If dark energy is not a cosmological constant but varies with time, or if gravity behaves differently from general relativity on cosmological scales, the Friedmann equation that maps redshift to age must be modified. Some of those modifications would make the universe older at a given high redshift, and others would make it younger. The direction of the modification matters for interpreting early galaxy observations. In early dark energy models, a component that briefly dominates the energy budget near the time of recombination changes the acoustic scale of the CMB and can be used to raise the inferred Hubble constant toward the locally measured value. But early dark energy also changes the expansion rate at intermediate redshifts in ways that affect the age at high redshift. In most early dark energy models, the effect on the age at z equals 14 is relatively small because the modification is concentrated near recombination, and the subsequent expansion follows the standard lambda CDM trajectory fairly closely. The age at extreme redshift is therefore not dramatically different from the standard prediction, even in models designed to resolve the Hubble tension. Phantom dark energy, where the equation of state parameter is below -1, leads to a future big rip, but also changes the current expansion rate in ways that affect the age-redshift relation. At very high redshifts, where matter dominates over dark energy, the differences between phantom and cosmological constant models are small, so the age at z equals 14 is not strongly affected by reasonable variations in the dark energy equation of state. This is actually a useful simplification, because it means the age at extreme redshift is relatively robust to dark energy uncertainties, even if it is less robust to Hubble constant uncertainties. Modifications to gravity on cosmological scales can have larger effects on the growth of structure than on the expansion rate itself, because many modified gravity theories maintain a similar expansion history to lambda CDM while predicting different rates of growth of density perturbations. The age-redshift relation follows the expansion history, not the growth rate, so modified gravity theories that preserve the expansion history also preserve the age estimates at high redshift. However, they change the predicted abundance of massive halos at those redshifts, which is a different kind of constraint on the early galaxy population. The consistency of the age estimate with other probes provides an important sanity check. The age of old stars in the local universe sets a lower limit on the age of the universe itself, and that lower limit must be consistent with the lambda CDM age. The ages of the oldest globular clusters in the Milky Way are estimated to be around 13 billion years, which is close to but slightly less than the lambda CDM age of the universe of 13.8 billion years. That consistency is reassuring, and it would be violated if lambda CDM were significantly wrong about the age. At high redshift, the equivalent check would be to find objects whose internal age is constrained, and to verify that their age is consistent with the time available between the Big Bang and the observed epoch. This is actually one of the constraints that early galaxy observations can provide. If a galaxy at z equals 14 contains a stellar population that is demonstrably older than 290 million years, then either the galaxy was formed before the Big Bang, which is impossible, or the redshift is wrong, or the age of the universe at that redshift is being underestimated. Finding a genuinely old stellar population at extreme redshift would be a direct challenge to the cosmic clock, more direct than finding chemical enrichment, because enrichment can in principle be rapid, while stellar ages cannot be sped up by astrophysical processes. Current observations do not show evidence of old stellar populations at z around 14, but the sensitivity to such populations is limited because old stars are faint in the ultraviolet, and the observations are primarily sensitive to the young massive stars that dominate the ultraviolet luminosity. The continuum shape from NIRCam photometry can in principle constrain the contribution from older stellar populations through the so-called bomber break and the shape of the rest frame optical continuum. But at these redshifts, disentangling the contributions of young and old stellar populations requires high signal-to-noise spectroscopy that is not yet available for most of the extreme high redshift candidates. The upper limit on the stellar age that can be derived from current data is therefore not very restrictive, meaning the presence of an older underlying population cannot be excluded by current observations. If such a population exists, it would imply that star formation began earlier than z equals 14, pushing the origin of the first stars to even higher redshifts. That would make the timeline even more compressed and would intensify the tension with standard early galaxy formation models. Or it could suggest that the galaxy was assembled from pre-existing stellar systems through mergers, in which case the stars were old before the merger occurred, and the galaxy itself is younger than the stars it contains. Mergers as an assembly mechanism for early galaxies are interesting in this context. Lambda CDM predicts that early galaxy assembly is dominated by mergers of smaller progenitors rather than by smooth accretion of gas. If two gas-spore stellar systems merge at Z around 14, the resulting object could contain an old stellar population, even though the galaxy as a currently observed entity did not exist until the merger. The merger could also trigger a new burst of star formation from any residual gas, producing the young massive stars needed for OII emission on top of the old underlying population. This would be a complex but not impossible scenario for producing a galaxy that appears both chemically enriched and dynamically assembled very early. The role of active galactic nuclei must also be considered in the context of early galaxy chemistry and the cosmic clock. Supermassive black holes are known to exist at redshifts above 7, where quasars with black hole masses of billions of solar masses have been found. The existence of these massive black holes so early in cosmic history is itself a challenge to standard models of black hole growth, which require either very heavy seed black holes or very rapid accretion or both. The connection between early black holes and early galaxies is bidirectional because black holes form in galactic nuclei and grow by accreting the same gas that fuels star formation. In the early universe, the radiation from an accreting black hole can significantly affect the surrounding gas. It can ionize the gas to higher states than stellar radiation alone, potentially exciting emission lines that would not otherwise be visible. It can also heat the gas and drive powerful outflows that expel both gas and metals. The balance between ionization and expulsion determines whether an active galactic nucleus in an early galaxy enhances or suppresses the detectability of emission lines like OII. In some geometries, the nuclear radiation can illuminate a large volume of the galaxy and produce very bright emission lines. In others, the outflows dominate, and the emission is suppressed or shifted to large velocity offsets. If the galaxy harboring the oxygen detection contains an active galactic nucleus, the emission line properties could be significantly different from what would be expected from star formation alone. The OII line can be excited by nuclear radiation as efficiently as by stellar radiation, and the line can appear strong even if the oxygen abundance is relatively low, because the nuclear source provides a much harder radiation field. Distinguishing between star formation and nuclear activity as the driver of the emission lines requires looking at line ratios, line widths, and the spatial extent of the emission, all of which are challenging to measure at these extreme distances. The Baldwin-Phillips-Sturlovich diagram, which uses ratios of different emission lines to distinguish between ionization by star formation and ionization by an active nucleus, is a standard tool at lower redshifts. Applying it at Z around 14 requires detecting multiple emission lines with sufficient precision to measure their ratios, which pushes the limits of current sensitivity. If the galaxy is powered by a buried active nucleus rather than by star formation, the interpretation of the oxygen detection changes substantially. The oxygen is still real, but the physical conditions producing the emission are very different, and the star formation history implied by the line strength must be revised. Early active galactic nuclei are not merely a complication for interpreting individual spectra. They are a fundamental part of the early galaxy formation story. The coevolution of black holes and galaxies, which is well established at lower redshifts through correlations between black hole mass and galaxy properties, must have had a beginning somewhere. The first massive black holes formed in the first galaxies, and their radiation and outflows shaped the chemical and dynamical evolution of those systems. Understanding the contribution of early active nuclei to the emission line signatures of extreme high redshift galaxies is therefore not just a technical correction, but a scientific question in its own right. The observational strategy for disentangling star formation from nuclear activity at extreme redshifts involves multiple emission line ratios, spatial resolution to determine whether the emission is concentrated in a nuclear point source or distributed across the galaxy, and variability measurements over timescales of months to years in the observer frame. Variability is a hallmark of active nuclei because the accretion process is inherently variable, while star formation is smoother on the relevant timescales. Webb can in principle detect variability in bright high redshift objects by observing them at multiple epochs separated by months, but interpreting the results requires accounting for the time dilation factor that stretches any variability timescale by a factor of 1 plus z at the source, at z equals 14. 32, the time dilation factor is about 15, meaning that a variability timescale of a year in the observer frame corresponds to only a few weeks at the source. Active nuclei can vary on weeks to months timescales in their rest frame, so year-scale observer frame monitoring could in principle detect variability associated with an active nucleus in a z equals 14 galaxy. Whether the source is bright enough to detect variability with statistical significance is another question that depends on the source flux and the background noise level, but it is a test worth pursuing with future Webb observations. The overall picture that emerges from this theoretical and observational analysis is one of genuine scientific progress balanced against genuine uncertainty. The oxygen claim at Z around 14 is a serious scientific statement that has motivated a productive re-examination of early galaxy formation physics. It has revealed that standard models may need revision at the extreme end of the early galaxy distribution, whether through a top-heavy initial mass function, bursty star formation, environmental effects, or some combination. It has also revealed that the measurement itself is at the edge of what is currently achievable, with multiple potential sources of systematic error that must be carefully evaluated. The productive tension between the claim and the model is the engine of progress. If the claim were trivially explained by existing models, it would not advance understanding. If it were simply wrong, it would waste telescope time and community attention. The most valuable situation is the one we appear to be in, where the claim is possibly right, possibly partially right, and possibly wrong in ways that teach us something. Each of those outcomes leads to better understanding of the early universe. The key is to continue the investigation with the combination of observational rigor and theoretical creativity that defines productive frontier science. The next generation of data will narrow the possibilities. More spectroscopic observations with longer integration times will improve the signal-to-noise on the putative features and search for additional lines. Independent analyses will test whether the features survive different reduction approaches. Larger survey samples will characterize the population statistics of early galaxies and test whether the oxygen galaxy is typical or exceptional. Complementary observations with ALMA and future facilities will probe the dust, molecular gas, and far-infrared properties that Webb cannot access. As those data accumulate, the mystery will narrow in the most satisfying scientific sense, not by being declared solved, but by having its uncertainty quantified more precisely. The question of whether oxygen can appear at 290 million years will move from provocative speculation to tested hypothesis to either confirmed phenomenon or instructive systematic error. And either outcome will advance the field's understanding of how the first galaxies built the chemical complexity that eventually made planets and life possible. The cosmic clock itself will continue to be tested by these observations and by the broader program of precision cosmology. The Hubble tension, the structure growth discrepancy, and the early galaxy brightness excess are all threads that pull on the same fabric. Whether they represent different symptoms of a single underlying problem or independent systematics in different measurements is a question that the next decade of observations will address. Lambda CDM has survived many such challenges in its history and has emerged stronger and better characterized each time. Whether it will survive the challenges of the Webb era or require fundamental revision is the deepest question that the oxygen galaxy has helped to crystallize. The theoretical landscape has been explored and the observational challenges have been cataloged. Now the story must turn to the specific techniques and future observations that will resolve the uncertainty surrounding the oxygen claim. Resolution does not come from a single measurement or a single paper. It comes from a convergence of evidence gathered through multiple independent approaches, each sensitive to different aspects of the physical system. Understanding what those approaches are and what they can realistically achieve is essential for knowing how long the mystery will persist and what form its resolution will take. The most direct path to resolution is additional spectroscopy of the galaxy itself. The current spectroscopic data, which forms the basis of the oxygen claim, represents a single observation with a specific integration time, instrument configuration, and data reduction pipeline. Each of those choices introduces potential biases that can only be characterized by repeating the observation under different conditions. A second independent spectrum, obtained with a different instrument setup or reduced with a different pipeline, would provide an immediate test of whether the claimed feature is robust or whether it depends on specific analysis choices. Webb's NIR-SPEC instrument has multiple observing modes that offer different trade-offs between spectral resolution, wavelength coverage, and throughupput. The microshutter assembly mode used for multi-object spectroscopy has different systematic properties from the fixed slit mode used for single bright objects and from the integral field unit mode used for spatially extended sources. If the oxygen feature appears consistently across multiple NIR spec modes, confidence in its reality rises substantially because the systematic errors in each mode are different, and a real feature should survive while an instrumental artifact should not. The spectral resolution also matters for line identification. At low resolution, a single broad feature might be the blended contribution of multiple lines, or it might be a noise spike that happens to be spectrally broad. At higher resolution, a real line should show a profile consistent with the gas velocity dispersion of the galaxy, while a noise spike should remain unresolved or show an irregular profile. In IR Spec's high-resolution mode, using the G395H or G235H gratings, provides resolving powers of 2 to 3000, which is sufficient to resolve the thermal and turbulent broadening expected for ionized gas in early galaxies. Detecting the oxygen line at high resolution and finding a physically reasonable line profile would be a significant step toward confirmation. The search for additional lines that should accompany the oxygen feature if the identification is correct is perhaps the most powerful test available with current technology. The OIII doublet consists of 2 lines at 4959 and 5007 angstroms in the rest frame, with a flux ratio of approximately 1 to 3. If the 5007 line is detected, the 4959 line should also be detectable at 1/3 the flux at a wavelength offset corresponding to the redshift of the doublet. Detecting both lines at the correct flux ratio and wavelength separation would be a much stronger confirmation than either line alone, because the probability that noise would produce 2 features at exactly the correct separation and ratio is very small. Other lines that should be present if the galaxy is truly at Z=14 and forming stars include hydrogen recombination lines like H-alpha at 6563 angstroms rest frame and H-beta at 4861 angstroms. These lines are produced when ionizing photons from massive stars are absorbed by hydrogen gas, which then recombines and cascades down through its energy levels, emitting photons at specific wavelengths. The ratio of H-alpha to H-beta, known as the Balmer decrement, is sensitive to dust extinction and provides an independent constraint on the reddening of the galaxy. At Z=14, H-alpha is shifted to observed wavelengths around 100 microns, which is in the far infrared and accessible only to ALMA rather than to Webb. H-beta at the same redshift falls around 79 microns, similarly beyond Webb's reach. This wavelength gap is one of the fundamental observational limitations at extreme redshifts. The rest frame optical lines that are most commonly used to characterize lower redshift galaxies are shifted into the far infrared and submillimeter at Z above 10, placing them beyond Webb sensitivity and into the territory of millimeter and submillimeter observatories. ALMA can in principle detect far-infrared fine structure lines from early galaxies, but its sensitivity at the relevant frequencies is limited by the thermal emission from the Earth's atmosphere and by the intrinsic faintness of the sources. The combination of Webb and ALMA observations therefore provides the most complete spectral characterization of extreme high redshift galaxies currently achievable. The far-infrared fine structure lines detectable with ALMA include the ionized carbon CII line at 158 microns rest frame, the oxygen OI line at 63 microns rest frame, and the ionized nitrogen NII lines at 122 and 205 microns rest frame. These lines are important diagnostics of gas conditions, ionization structure, and chemical abundance, and they are complementary to the near-infrared optical lines accessible to Webb. The CII line is particularly valuable because it is typically the brightest far-infrared line in star-forming galaxies, and it traces both ionized and neutral gas phases. At Z=14, the CII line falls at observed wavelengths around 24 millimeters, which is in the ALMA band 2 range, and represents one of the most challenging ALMA observations currently conceivable. Detecting the CII line in a galaxy at Z=14 would require extremely long integration times with ALMA, likely more than 100 hours even for the brightest predicted sources. That kind of investment requires strong motivation from the prior optical and near-infrared characterization, which means the sequence is necessarily Webb first, then ALMA follow-up. The integration times required also mean that only a handful of the most compelling targets can be observed in this way, and the selection of those targets must be made carefully to maximize the scientific return. If both Webb optical and ALMA far-infrared lines can be detected, and the redshift confirmed from multiple independent line identifications, the confidence in the galaxy's properties would be transformative. The combination of lines covering different ionization states and gas phases would constrain the physical conditions in the galaxy's interstellar medium with a detail that is currently available only for nearby galaxies. That level of characterization would make it possible to definitively determine the oxygen abundance, the ionization parameter, the gas density, and the dust-to-gas ratio, and to compare those properties against theoretical predictions with much greater precision than the current data allow. Gravitational lensing is another path to enhance sensitivity that does not require waiting for larger telescopes. When a background galaxy is aligned with a massive foreground object like a galaxy cluster, the cluster's gravity bends and magnifies the background galaxy's light. The magnification can be factors of 10, 50, or even higher in the most extreme cases, effectively multiplying the collecting area of Webb by the same factor for that specific source. Lensed high-redshift galaxies are therefore scientifically extremely valuable because they provide access to physical conditions that would otherwise require much larger telescopes. Several of the most well-characterized high-redshift galaxies known to date are lensed objects, including some of the early Webb spectroscopic conformations at redshifts above 10. The challenge for extreme high-redshift objects like the Z=14 galaxy is that suitable lensing configurations are not guaranteed. The galaxy must happen to lie behind a massive foreground cluster at the correct alignment to produce high magnification. That alignment is relatively rare, and searching for lensed analogs of the oxygen galaxy requires wide-field surveys that cover enough sky to find the rare fortunate alignments. The Hubble Space Telescope's Frontier Fields program surveyed 6 massive galaxy clusters specifically to find highly magnified background galaxies, and that program produced some of the most detailed observations of high-redshift galaxies available before Webb. Webb has continued and extended that approach, observing known massive clusters to find lensed sources at extreme redshifts. The sensitivity advantage from lensing magnification compensates for the reduced volume surveyed, making cluster fields complementary to blank field surveys for characterizing the early galaxy population. If a lensed analog of the oxygen galaxy at Z=14 were found with magnification of 20 or 50, the effective signal-to-noise ratio for spectroscopy would be dramatically higher, making it possible to detect weaker lines, measure line ratios, and characterize the line profiles with a detail that is currently impossible for unlensed sources. A magnified source would also allow the spatial distribution of emission to be studied, revealing whether the oxygen emission is concentrated in a nuclear region, distributed across the galaxy, or associated with specific star-forming clumps. That spatial information would constrain the physical mechanism responsible for the enrichment in ways that integrated spectroscopy cannot. The next generation of ground-based extremely large telescopes will provide another major capability advance for following up on early Webb discoveries. The 30-meter telescope, the Giant Magellan Telescope, and the Extremely Large Telescope, currently under construction in Chile, will have primary mirrors ranging from 24 to 39 meters in diameter, collecting areas that exceed Webb by factors of tens to hundreds. With adaptive optics systems that correct for atmospheric blurring, these telescopes will be able to achieve angular resolutions comparable to or better than Webb at certain wavelengths. The collecting area advantage of the extremely large telescopes is decisive for spectroscopy of faint objects. Spectroscopy is fundamentally a photon-limited exercise because the light must be dispersed across many wavelength channels, reducing the flux in each channel. Larger mirrors collect more photons per unit time, allowing higher signal-to-noise ratios in shorter integration times or equivalent signal-to-noise ratios for much fainter objects. For the oxygen galaxy at Z=14, an extremely large telescope could potentially detect the same spectral features that Webb sees with much higher signal-to-noise ratios, resolving the question of whether the features are real and providing precise measurements of line ratios and profiles. The extremely large telescopes will also have spectrographs with higher spectral resolution than Webb's NIRS-spec in some modes. High spectral resolution is valuable for measuring the kinematics of the galaxy's gas, including rotation, turbulent motion, and outflows. At extreme redshifts, kinematic measurements can constrain the dynamical mass of the galaxy, providing an independent estimate of the gravitational potential that hosts the star formation. If the dynamical mass is consistent with a halo massive enough to retain metals against supernova feedback, the physical scenario for early enrichment becomes more internally consistent. The timeline for the extremely large telescopes is relevant to the oxygen mystery. The Extremely Large Telescope in Chile is expected to achieve first light in the late 2020s, with full capability arriving in the early 2030s. The Giant Magellan Telescope has a similar timeline. The 30-meter telescope faces regulatory challenges that have complicated its schedule, but it is also expected to be operational within the next decade under optimistic scenarios. Within roughly 10 years, therefore, the observational tools needed to definitively characterize the extreme high redshift galaxy population should be available. In the interim, Webb itself continues to accumulate data. The telescope's operational lifetime is extended by the precision of its launch, which conserved fuel that would otherwise have been spent correcting trajectory errors. Current estimates suggest that Webb has enough propellant for potentially 20 or more years of operation, far exceeding the design goal of 10 years. That extended operational lifetime means that the current dataset represents only the beginning of what Webb will eventually produce. As survey strategies are refined and the most productive targets are identified, the characterization of early galaxies will continue to improve even before the extremely large telescopes come online. Webb's director's discretionary programs and guest observer programs have already demonstrated the value of flexibility in targeting. When a particularly promising result like the oxygen detection emerges, the community can propose and receive additional telescope time to follow up with higher priority than the regular allocation process would allow. This responsive approach to targeted opportunity science is important at the frontier because the most important results are by definition not anticipated in advance. The ability to quickly mobilize additional resources toward compelling targets is a feature of modern observatories that amplifies their scientific productivity beyond what their initial designs specified. The theoretical community must also continue developing better models that can make specific testable predictions for what future observations should find. The current generation of simulations has provided valuable qualitative insights, but is limited in its quantitative precision at the extreme high redshift frontier. The next generation of simulations must achieve both the volume needed to find rare massive halos and the resolution needed to model the internal physics of early galaxies. That combination requires computational resources that are currently pushing the limits of available hardware, and advances in computing technology will be as important as advances in telescope technology for making progress on this problem. Specifically, simulations need to improve their treatment of population III stars and the transition from primordial to metal-enriched star formation. The first enrichment events set the conditions for everything that follows, and the uncertainty in how they unfold propagates into uncertainty about when and how galaxies like the oxygen source could have assembled their chemistry. Better models of the first stars, including their mass distribution, their feedback mechanisms, and the efficiency with which their ejecta mixes into surrounding gas, are needed to narrow the theoretical uncertainty about early enrichment timescales. The observational constraints on population III stars themselves are an important input to those models. Population III stars have not been directly detected because individual stars in early galaxies are far too faint to observe. But they may leave detectable signatures through the chemical patterns they imprint on subsequent stellar generations. Metal-poor stars in the Milky Way halo, which formed from gas that was enriched by only a few early supernova events, preserve chemical abundance patterns that carry information about the masses and yields of the enriching population III stars. Studies of extremely metal-poor halo stars, sometimes called near-field cosmology because they probe the early universe through nearby ancient objects, provide crucial constraints on early stellar physics that feed into models of high-redshift galaxies. The connection between near-field cosmology and far-field cosmology, meaning between the study of ancient stars in our own galaxy and the study of distant early galaxies with Webb, is one of the most intellectually productive connections in contemporary astrophysics. Both approaches are asking the same fundamental question about when and how the universe built its first heavy elements. The near-field approach has the advantage of very detailed chemical abundance measurements because the individual stars can be studied at high spectral resolution with ground-based spectrographs. The far-field approach has the advantage of directly observing the process as it occurs, rather than reconstructing it from its aftermath billions of years later. Combining the two perspectives is more powerful than either alone. The stellar abundance patterns in metal-poor halo stars suggest that the first enriching supernovae were from massive stars, consistent with the theoretical expectation of a top-heavy population II initial mass function. The specific patterns, including the ratios of carbon, oxygen, magnesium, and iron, encode information about the masses of the progenitor stars and the explosion energies of the supernovae. Hypernova, which are extremely energetic explosions from the most massive stars, produce distinctive abundance ratios that appear in many of the most metal-poor stars. If the first enrichment events in high-redshift galaxies were dominated by hypernova, the rapid oxygen production needed to explain the emission line detection would be more naturally explained. The connection between hypernova yields and early galaxy chemistry is a specific theoretical prediction that bridges the near-field and far-field perspectives. If the initial mass function in early galaxies was top-heavy and dominated by massive stars that ended as hypernova, the chemical signature in the gas would be enhanced in oxygen and other elements produced in large quantities by those explosions. That enhancement would make the OIII line brighter for a given total metal content, because a higher fraction of the metals would be in the form of oxygen rather than in heavier elements like iron. In other words, hypernova would make early galaxies more oxygen-rich per unit total metallicity than standard supernova yields would predict. This prediction is testable in principle through measurements of the ratio of different metal emission lines. The ratio of oxygen lines to iron lines, for example, encodes the oxygen-to-iron ratio in the gas, which is sensitive to the relative contributions of core collapse supernovae and type Ia supernovae. Type Ia supernovae produce large amounts of iron with relatively little oxygen, while core collapse supernovae and hypernova produce large amounts of oxygen with relatively little iron. At very early times before the first type Ia supernovae have had time to explode, the oxygen-to-iron ratio should be high, reflecting the dominance of core collapse events. If the oxygen galaxy shows evidence of a high oxygen-to-iron ratio, it would be consistent with enrichment by an early generation of massive stars before type Ia supernovae began contributing. Measuring iron line emission in a galaxy at Z equals 14 is currently beyond reach because the relevant iron lines in the rest frame ultraviolet and optical are faint and would require extremely high signal-to-noise spectroscopy. But future extremely large telescope observations could in principle achieve the sensitivity needed to detect or place meaningful upper limits on iron emission in the brightest early galaxy candidates. Those measurements would be transformative for understanding the early chemical enrichment history and would directly connect far-field galaxy observations to near-field stellar abundance studies. The broader program of connecting early universe observations to the detailed chemical record preserved in old stars is one of the most exciting scientific frontiers of the coming decade. Webb is opening one end of this program by providing direct observations of galaxies at the epoch of first light. Ground-based spectrographs are advancing the other end by measuring chemical abundances in increasingly metal-poor halo stars with increasingly high precision. The two lines of evidence are converging on the same physical question, and their convergence will eventually produce a coherent picture of how the first stars and galaxies built the chemical complexity of the universe. The Milky Way itself is a fossil record of its own assembly history, and modern surveys of its stellar populations are extracting that record with increasing detail. The Gaia satellite has mapped the positions and motions of over 1 billion stars in the galaxy, revealing the structure of its various components and the signatures of past merger events. Spectroscopic surveys like the Galactic Archaeology with Hermes Survey, the Apache Point Observatory Galactic Evolution Experiment, and the JWST Enhanced Area Velocity Explorer are measuring chemical abundances for millions of stars, building a chemical map of the galaxy that can be used to infer its formation history. The oldest, most metal-poor stars in those surveys are the most direct link to the epoch of first galaxy formation. The chemical patterns in those ancient stars are being compared with theoretical models of early enrichment, and the comparison is beginning to constrain the properties of the first stellar generations. The emerging picture suggests that the first enriching events were indeed from massive short-lived stars that produced oxygen-rich ejecta. The transition to more iron-rich enrichment from type Ia supernovae occurred later, after the galaxy had already accumulated significant stellar mass. This sequence is consistent with the general scenario invoked to explain the oxygen detection in the high-redshift galaxy, although the quantitative details of when and how fast this transition occurred are not yet precisely established. The timing of the type Ia supernova onset is a key parameter in this context. Type Ia supernovae arise from white dwarfs in binary systems, and the delay time between the formation of the binary system and the supernova event can range from a few 100 million years to several billion years. At Z equals 14, Even the shortest delay time white dwarfs would not yet have contributed to enrichment if the galaxy's stellar populations formed very recently. The iron content of the galaxy's gas would therefore reflect only core collapse and hypernova contributions, making the gas oxygen-enhanced relative to solar abundances in the same way that metal-poor halo stars are oxygen-enhanced. This prediction of oxygen enhancement in the earliest galaxies is a specific and testable consequence of the enrichment sequence. It means that the oxygen-to-metal ratio in very early galaxies should be higher than in later galaxies, where type Ia supernovae have had time to contribute iron. If the oxygen detection is characterized as an oxygen-to-metal ratio rather than just an oxygen detection, it should be consistent with this prediction. If instead the oxygen-to-metal ratio appears solar or below, it would imply that the enrichment history is more complex than expected, with type Ia supernovae contributing earlier than the delay time distribution suggests, or with some other source of iron that operates on shorter timescales. Early black hole formation and the associated metal enrichment from nuclear outflows is one such alternative source. Active galactic nucleus winds can be highly enriched in metals produced in the accretion disk or in the surrounding starburst, and these winds can distribute metals throughout the galaxy and even into the circumgalactic medium. If the accretion disk produces iron-rich material as part of the disk chemistry, the resulting enrichment pattern could be different from what pure stellar nucleosynthesis would predict. Disentangling nuclear enrichment from stellar enrichment at extreme redshifts is another frontier problem that future high-resolution spectroscopy must address. The spatial distribution of the emission provides one lever for this disentanglement. Stellar enrichment should produce emission that is distributed across the star-forming regions of the galaxy, following the distribution of ionized gas clouds. Nuclear enrichment should produce emission that is more concentrated toward the galaxy's center, tracing the influence of the active nucleus and its outflows. At z=14, the galaxy is so distant that even with Webb's angular resolution, spatially resolving the emission distribution requires either gravitational lensing magnification or a galaxy that is intrinsically extended and bright enough to characterize with current sensitivity. The picture that emerges from all these considerations is one of extraordinary scientific richness surrounding a single spectral feature. The oxygen line, if real, is not merely evidence of chemical enrichment. It is a convergence point for multiple lines of research, each of which is progressing with its own tools and methods. The convergence is not yet complete, but it is advancing rapidly, and the pace of progress suggests that the fundamental questions about early galaxy chemistry will be substantially resolved within the next decade through the combination of Webb's continued observations, ALMA follow-up, extremely large telescope spectroscopy, and improved theoretical models calibrated against both far-field and near-field observations. Having examined the future observations and theoretical connections, the story must now address what is perhaps the most philosophically interesting aspect of the mystery. The cosmic clock and the interpretation of extreme high redshift observations are not independent. They are connected through the cosmological model in a way that makes it genuinely difficult to know whether a surprising observation reflects new physics or incorrect assumptions. That circularity is not a failure of method, but an inherent feature of observational cosmology at the frontier, and understanding it is essential for evaluating claims like the oxygen detection with appropriate skepticism and appropriate openness. The circularity works as follows. We observe a spectrum and assign a redshift. The redshift is converted to an age using lambda CDM. The age determines whether the observed chemistry is surprising. If it is surprising, we can either revise the chemistry claim, revise the astrophysical model, or revise the cosmological model. The cosmological model itself is tested against the same observation that is being interpreted, creating a loop where the evidence and the framework that interprets the evidence are not fully independent. This is not unique to cosmology. All of science involves frameworks for interpreting observations, and those frameworks are never fully decoupled from the observations they interpret. What makes cosmology particularly challenging is that the framework, lambda CDM, is built on a relatively small number of extremely powerful observations, primarily the CMB, the baryon acoustic oscillations, and the supernova distance measurements. Those observations constrain the cosmological parameters tightly enough that the framework feels like solid ground, but they still leave room for the framework to be wrong in ways that would affect interpretation of extreme high redshift objects. The CMB is the most powerful single constraint on the cosmological parameters. Its temperature fluctuation pattern encodes the density of baryons, cold dark matter, and photons at the time of recombination, and the peaks and troughs of that pattern are sensitive to the relative contributions of these components. The CMB also constrains the geometry of the universe, the total energy density, and the spectral index of the primordial fluctuations. These constraints are so tight that varying individual parameters, while holding the CMB fixed, leaves very little room for the expansion history to differ significantly from the lambda CDM prediction. However, the CMB is a measurement of the universe at one specific epoch, roughly 380,000 years after the Big Bang. To extrapolate from that epoch to z equals 14, which is several hundred million years later, requires assuming that the physics governing the expansion and structure growth is the same throughout that interval. In lambda CDM, that assumption is built in because the relevant physics, general relativity plus the specific matter content, is assumed to be valid at all times. If there were new physics active between recombination and z equals 14, the extrapolation from the CMB to that epoch could be incorrect. The window between recombination and the epoch of the oxygen galaxy is a relatively unexplored regime in observational terms. Direct probes of this interval include measurements of the intergalactic medium's neutral fraction from quasar absorption spectra, which trace reionization, and 21 centimeter radiation from neutral hydrogen, which in principle traces the distribution of neutral gas throughout the cosmic dark ages and the epoch of reionization. The 21 centimeter signal from the early universe is extraordinarily difficult to detect because it is mixed with much brighter foreground emission from our own galaxy and other sources. But experiments like the hydrogen epoch of reionization array and future instruments like the square kilometer array are working to detect this signal. If the 21 centimeter signal from the epoch between z equals 20 and z equals 6 is detected and characterized, it would provide a direct measurement of the state of the intergalactic medium throughout the interval that includes the oxygen galaxy's epoch. That measurement would constrain when reionization began, how fast it progressed, and what sources drove it. Those constraints would in turn inform models of early galaxy formation and would help calibrate the theoretical expectations for early chemical enrichment. A 21 centimeter detection, consistent with standard lambda CDM reionization, would reduce the theoretical uncertainty around the oxygen claim. A detection inconsistent with standard expectations would open new questions about the early universe that could affect the interpretation of the oxygen spectrum. The EDGES experiment, which searches for the globally averaged 21 centimeter signal, reported a tentative detection in 2018 that was much stronger than standard models predicted. If confirmed, that detection would suggest either that the early intergalactic medium was colder than expected or that there was an additional radio background present in the early universe. Both interpretations have significant implications for early galaxy formation and for the physics of the first stars. However, the EDGES result has not been confirmed by independent experiments, and its significance remains debated. A confirmed anomalous 21 centimeter signal would be a major discovery that would force a fundamental revision of early universe physics and would add another dimension to the interpretation of high redshift galaxy observations. The interplay between the 21 centimeter signal and the high redshift galaxy observations illustrates the principle that major discoveries in frontier science are rarely isolated. They come in clusters, with multiple lines of evidence converging on the same questions from different directions. The oxygen galaxy claim is one thread in a larger tapestry that includes the Hubble tension, the early galaxy brightness excess, the EDGES anomaly, the discovery of massive early black holes, and the unexpected properties of early galaxy morphologies revealed by Webb. Each thread is uncertain on its own, but if they consistently point in the same direction, the coherent picture they create carries much more weight than any individual thread. Currently, it is not clear that all these threads consistently point in the same direction. The Hubble tension could reflect new physics between recombination and today, or it could reflect systematic errors in distance measurements. The early galaxy brightness excess could reflect astrophysics within standard cosmology, or it could reflect a genuinely higher abundance of early massive halos. The EDGES anomaly could be a real early universe signal or an instrumental artifact. The oxygen detection could be a genuine physical phenomenon or a systematic error in the spectrum. The fact that multiple potential anomalies exist does not necessarily mean they share a common explanation. Unrelated anomalies can accumulate coincidentally, and the temptation to weave them into a single narrative should be resisted until the evidence for each is independently solid. But the coincidence of multiple potential anomalies in the same cosmic epoch is worth taking seriously as a research strategy. If several independent measurements all show hints of unexpected behavior in the early universe, the most productive scientific response is to design observations that can test whether the anomalies are real and whether they share a common origin. That strategy is already being pursued through the combination of Webb observations, CMB experiments, 21-centimeter telescopes, baryon acoustic oscillation surveys, and gravitational wave observatories that together probe the early universe from multiple independent angles. Gravitational waves from the early universe provide yet another potential window on the physics of the first hundreds of millions of years. The Laser Interferometer Space Antenna, scheduled for launch in the 2030s, will be sensitive to gravitational waves from massive black hole mergers across cosmic history, including the first mergers at high redshift. Those mergers produce gravitational wave signals that carry information about the masses and spins of the merging objects, and the distribution of merger events across redshift encodes information about how massive black holes assembled in the early universe. If black hole mergers at Z above 10 are detected by LISA, and their properties are compared with the galaxy populations found by Webb, the combined picture of how galaxies and black holes co-evolved in the early universe will be dramatically more detailed than what any single instrument can provide. The pulsar timing array experiments, which use millisecond pulsars as cosmic clocks to detect very low-frequency gravitational waves, have recently reported evidence for a gravitational wave background. This background could originate from a population of supermassive black hole binaries across cosmic history, including contributions from early high redshift mergers. The spectral shape and amplitude of the background encodes statistical information about the merger history that complements the individual event detections that LISA will provide. If the pulsar timing background is inconsistent with standard models of supermassive black hole formation and merger, it would add another potential thread to the tapestry of early universe anomalies. The Square Kilometre Array, which is currently under construction in South Africa and Australia, will have the sensitivity to detect pulsars throughout the galaxy and will dramatically extend the pulsar timing array measurements. It will also conduct surveys of neutral hydrogen through the 21-centimeter line at unprecedented depth and resolution, probing the large-scale distribution of matter and the state of reionization across the relevant redshift range. The combination of SKA pulsar timing, SKA hydrogen surveys, Webb galaxy observations, and CMB measurements from next-generation experiments like the Simons Observatory and CMB-S4 will provide a comprehensive observational characterization of the early universe that is currently inconceivable. CMB-S4, a proposed ground-based observatory that would use thousands of detectors to map the CMB with unprecedented sensitivity, would provide measurements of the CMB's polarization pattern at small angular scales that are currently unmeasured. Those measurements would constrain the optical depth to reionization with higher precision, improving our knowledge of when reionization occurred and how quickly it proceeded. They would also search for primordial gravitational waves from inflation, which would constrain the energy scale of inflation and the physics of the very early universe. Detecting primordial gravitational waves would be one of the most significant discoveries in the history of cosmology, as it would provide a direct window on physics at energy scales far beyond what particle accelerators can probe. The connection between primordial gravitational waves and the oxygen galaxy might seem remote, but it is real. The energy scale of inflation determines the amplitude of primordial density fluctuations on all scales, including the small scales relevant to the formation of the first galaxies. A higher inflationary energy scale corresponds to more primordial gravitational waves and potentially a somewhat different power spectrum of density fluctuations on scales relevant to early structure formation. Precise measurements of the primordial power spectrum across a wide range of scales, from the large scales measured by the CMB to the small scales relevant to the first galaxies, would constrain the properties of inflation in ways that feed into predictions for the early galaxy population. This connection between inflation and early galaxy formation is one of the deepest theoretical links in observational cosmology. Inflation sets the initial conditions for everything that follows, including the seeds of the first galaxies. Understanding those initial conditions more precisely would reduce the theoretical uncertainty about the predicted early galaxy population and would sharpen the comparison between observation and theory that is currently limited by both observational uncertainty and theoretical imprecision. The oxygen claim at Z equals 14 is therefore not just a local curiosity about one galaxy's chemistry. It is a probe of physics that extends all the way back to the first moments of the universe's existence. The multi-messenger and multi-wavelength approach to understanding the early universe represents a fundamental shift in the methodology of frontier cosmology. The era of single-instrument discoveries that define a field is giving way to an era where the most important questions can only be answered by combining independent measurements from facilities that are sensitive to different physical processes. That integration requires coordination across different scientific communities, different observatories, and different analytical traditions, each with its own culture and methodology. The oxygen galaxy at Z around 14 is an example of an observation that is already motivating exactly that kind of integration. Its apparent properties have prompted discussions between astronomers who study high-redshift galaxies with Webb, theorists who model early galaxy formation and chemical enrichment, observers who study metal-poor halo stars as chemical fossils, and cosmologists who work on the lambda CDM parameter estimates that provide the cosmic clock. Each of these communities brings a different perspective and different expertise, and the dialogue among them is producing more sophisticated understanding of the problem than any single community could achieve alone. The integration of these communities is not always smooth. Different fields have different standards of evidence, different vocabularies, and different intuitions about what constitutes a compelling result. The early galaxy observers who work with Webb data are accustomed to the challenges of faint source detection and the provisional nature of high redshift photometric redshifts. The chemical evolution modelers are accustomed to working with uncertain stellar yields and incomplete observational constraints on star formation efficiency. The cosmologists who interpret lambda CDM parameter estimates are accustomed to statistical rigor and careful error propagation across large data sets. When these communities engage on a common problem, the result is sometimes productive friction that sharpens understanding and sometimes genuine confusion about whether different groups are even asking the same question. The oxygen claim has generated exactly this kind of productive friction. Observers who initially reported the result applied the standards of their field, reporting the significance of the spectral feature and the best fit redshift with appropriate caveats. Theorists who responded to the claim applied the standards of their field, testing whether the result was consistent with existing models and identifying the physical conditions that would be required to explain it. Cosmologists who engaged with the implications applied their standards, testing whether the claim required modifications to lambda CDM and characterizing the observational constraints that any alternative model must satisfy. The friction among these perspectives is not a problem to be solved, but a resource to be managed. It motivates clearer communication, more careful definition of what is claimed and what is assumed, and more explicit statement of which aspects of a result depend on which underlying assumptions. When a claim at the edge of the universe is examined by multiple communities with different tools and different priors, the result is a more robust assessment of its significance and its implications than any single community's evaluation would provide. The oxygen claim is still in the early stages of this multi-community evaluation. The initial report has attracted attention and generated responses. Additional observations are being planned, theoretical models are being tested, statistical analyses of the broader population are being conducted. The process is ongoing and its outcome is not yet determined. But the process itself is a demonstration of how frontier science works, not through a single eureka moment, but through an accumulating consensus that forms over time through the contributions of many researchers approaching the same question from many angles. That accumulating consensus is the most reliable path to truth in science, even when it is slow and sometimes frustrating. The oxygen claim at Z equals 14 will either join the record of confirmed cosmic discoveries or will join the equally valuable record of systematic errors caught and corrected by careful science. Either outcome advances understanding. Either outcome provides a clearer view of the early universe and a better calibration of the methods used to observe it. The investigation is worthwhile regardless of how it resolves, which is why the question deserves the careful, multifaceted examination it is currently receiving. The investigation has been laid out in its full complexity. The measurement, the physical implications, the cosmological context, the alternative explanations, the future observations, and the philosophical framework have all been examined. Now the story must return to its beginning and ask what all of this means for our understanding of the universe and its earliest moments. The oxygen galaxy is not merely a scientific puzzle to be solved. It is a reflection of where cosmology stands at this particular moment in its history, at the junction between unprecedented observational capability and incomplete theoretical understanding. Webb represents the culmination of a remarkable period in human technological achievement. The ability to collect and analyze photons that have been traveling for more than 13 billion years, to read in those photons the signatures of atoms excited in galaxies that existed when the universe was a fraction of its current age, is an accomplishment that would have seemed like science fiction to the astronomers of a generation ago. The telescope's existence is a testament to the collective investment that societies make in understanding where they came from, and its results are a partial repayment of that investment in the form of new knowledge about the universe's history. That new knowledge is inherently incomplete because the universe is under no obligation to arrange itself for our convenience. The most interesting questions are always at the edge of what is currently measurable, where the signal is faint and the systematic errors are large and the interpretation is model-dependent. The oxygen galaxy sits at exactly that edge, making it simultaneously the most exciting kind of result and the most provisional kind of result. It is exciting because it challenges expectations and opens new questions. It is provisional because the evidence is not yet strong enough to settle those questions definitively. The appropriate response to such a result is precisely what the scientific community has been doing. Taking it seriously enough to invest significant resources in follow-up observations and theoretical work, maintaining enough skepticism to insist on independent confirmation and careful error analysis, and keeping sight of the larger questions that the result illuminates about the pace of early star formation, the efficiency of early chemical enrichment, and the reliability of the cosmological framework that gives the observation its dramatic character. The cosmic clock that the oxygen claim stresses is not a fragile instrument. It is built on solid foundations of general relativity, quantum mechanics, and a century of observational cosmology, but it is also not perfect. Its precision is limited by the precision of the measurements that constrain its parameters, and those measurements have their own uncertainties and potential systematics. The Hubble tension is a reminder that the clock is still being calibrated, and that the calibration effort is revealing tensions that may reflect new physics or may reflect uncharacterized errors in the measurements themselves. The early universe is the ultimate testing ground for the cosmic clock because it is the regime where the clock's inputs, the initial conditions from the CMB, and the subsequent evolution under lambda CDM, are most directly tested against observations of the objects that those inputs predicted. When Webb finds galaxies that seem to challenge those predictions, the response should be neither to defend the model reflexively nor to abandon it prematurely, but to demand better data and more careful analysis that can distinguish between the possibilities. The oxygen galaxy at Z equals 1432 is a demand for exactly that kind of better data and more careful analysis. It is a question posed to the universe and to the community of researchers who study it. The answer will come not from any single observation or any single paper, but from the patient accumulation of evidence that is the hallmark of mature empirical science. The journey toward that answer is already underway, and it will define some of the most productive and revealing years in the history of observational cosmology. As Webb continues to survey the early universe, and as the theoretical community continues to refine its models, and as new facilities come online to complement Webb's observations, the picture of the first galaxies will become progressively clearer. The oxygen mystery will resolve. The cosmic clock will be better calibrated. The initial mass function of the first stars will be better constrained. The efficiency of early chemical enrichment will be measured against the backdrop of the lambda CDM structure growth predictions. And the first galaxies will gradually transform from mysterious smudges at the edge of the observable universe into understood physical systems whose properties we can explain from first principles. That transformation is the ultimate goal of all the observations, the theoretical work, and the technological investment that the oxygen claim has brought into focus. It is the goal of knowing the universe not just as a spectacle to be marveled at, but as a physical system to be understood. The oxygen in the spectrum of a galaxy 4 billion light-years away, is not just a chemical fingerprint. It is a connection between the cosmos and the chemistry of life, a reminder that the oxygen in every breath traces its origin through stellar generations that began in exactly the kind of violent, efficient, early star formation that the oxygen galaxy appears to represent. Whether that galaxy truly formed its oxygen in less than 300 million years, or whether the signal reflects a lower redshift or a different chemical identification, the investigation it has motivated is advancing understanding of how the universe built its complexity from simplicity. That understanding is one of the great intellectual achievements of our era, and it is being assembled piece by piece, photon by photon, spectrum by spectrum, in the most ambitious and productive era of observational cosmology that humanity has ever experienced. The cosmic clock ticks on, and with each Webb observation, our ability to read it becomes more precise, more reliable, and more deeply connected to the physical reality of the universe we inhabit. The mystery of the oxygen galaxy will be solved. Not with a single dramatic revelation, but with the quiet, cumulative progress of careful science at the frontier of human knowledge. And when it is solved, it will reveal not just the truth about one galaxy's chemistry, but something deeper about the pace and character of the universe's first creative act, the forging of complexity from simplicity, of chemistry from physics, and of structure from the formless uniformity of the cosmic beginning. That is what a thin line in a spectrum carries when it sits at the edge of the observable universe. Not just data, but a question about origins that reaches all the way back to the first moments of time. The investigation has reached its deepest theoretical and observational layers. Now the story must pull back from the details and survey the broader intellectual landscape that the oxygen claim inhabits. That landscape is defined not just by the specific measurements and models that have been examined, but by the history of how cosmology has responded to previous surprises at the frontier, and by what that history teaches us about how to evaluate the current situation with appropriate perspective. Cosmology has a long and instructive history of results that initially appeared to challenge the prevailing framework, and that eventually resolved in one of three ways. Some resolved by confirming the challenge and forcing a genuine revision of the model. Some resolved by revealing systematic errors in the observations that made the challenge disappear. And some resolved in a subtler third way, where the challenge was real, but the revision required was smaller and more surgical than the initial alarm suggested. Understanding which category the oxygen claim falls into requires understanding the patterns of how such situations have played out before, because those patterns provide calibration for how much weight to assign to the current situation. The discovery of cosmic acceleration in the late 1990s is the most dramatic example of the first category, a genuine challenge that forced a genuine revision. Before that discovery, the prevailing view was that the universe's expansion was slowing down due to the gravitational pull of matter. The cosmological constant, which Einstein had introduced and then abandoned, was generally considered either zero or negligible. When two independent teams measuring the distances to Type Ia supernovae at high redshifts found that the supernovae were fainter than expected, implying they were farther away than a decelerating universe would place them, the initial reaction was skepticism. The result was so unexpected and so consequential that extraordinary evidence was demanded before it could be accepted. The evidence accumulated over the following years from multiple independent sources. The CMB measurements, which were improving rapidly around the same time, showed that the universe was geometrically flat, requiring a total energy density equal to the critical density. Since the measured matter density was only about 30% of critical, something else had to make up the remaining 70%. The combination of supernova distances requiring acceleration and CMB geometry requiring a missing component pointed to the same answer from two completely independent directions. Lambda CDM with a cosmological constant was not just consistent with the supernova data. It was required by the combined weight of evidence from completely different physical probes. The lesson from that episode is that genuine revisions to the cosmological framework are typically confirmed not by a single striking result, but by the convergence of multiple independent lines of evidence on a common conclusion. The oxygen claim has so far generated one striking result and a context of related surprises, but it has not yet achieved the level of multi-line convergence that marked the acceptance of cosmic acceleration. That does not mean the oxygen claim is wrong. It means it has not yet accumulated the weight of evidence needed to revise the framework. The process of accumulation is underway, but it is not complete. The second category, challenges that resolved by revealing systematic errors, is represented by several episodes in the history of high redshift galaxy observations. The history of claimed record-breaking redshifts is particularly instructive. Throughout the 1990s and 2000s, a succession of galaxies and quasars were claimed as the most distant known objects, each one briefly holding the record before being superseded by a more distant candidate, or, in some cases, before being revised to a lower redshift when better data arrived. Several of these revisions were embarrassing in hindsight because the original claims had been made with high confidence based on what turned out to be inadequate data or insufficient attention to alternative explanations. The pattern of record claims followed by revisions is not evidence that high-redshift astronomy is unreliable. It is evidence that the field is actively pushing to the edge of what is observable, and that the edge is precisely where systematic errors are most likely to produce misleading results. The revisions themselves are a sign that the community's self-correction mechanisms are working. When independent observers with better data or better analysis tools find that a claimed redshift is incorrect, the correction is published and the community updates its understanding. The process is slower and messier than an idealized picture of science would suggest, but it is effective in the long run. The current situation with extreme high redshift candidates from Webb has already shown elements of this pattern. Several galaxies that were initially reported with photometric redshifts above 15 have been revised to lower redshifts, sometimes substantially lower, when spectroscopic confirmation was obtained. The revisions are consistent with known biases in photometric redshift estimation at the detection limit and do not represent failures of the underlying science. They represent the expected behavior of methods that are being pushed beyond their validated range. The oxygen claim, which is based on spectroscopic data rather than purely photometric estimates, is in principle more robust than purely photometric claims, but it is not immune to the kinds of systematic errors that have affected other high redshift claims. The third category, challenges that are real but require smaller revisions than initially feared, is perhaps the most common outcome and the most instructive for thinking about the current situation. Many of the most prominent tensions in cosmological history have ultimately resolved in this way. The discrepancy between the ages of the oldest stars and the age of the universe inferred from the Hubble constant was a tension that persisted through much of the 1980s and early 1990s. The stellar ages seemed to exceed the cosmic age by an uncomfortable margin, suggesting something was wrong with the expansion rate or the stellar models or both. The resolution came from multiple directions simultaneously. Improved stellar models revised the ages of old stars downward slightly. More precise Hubble constant measurements moved the expansion rate into a range more consistent with stellar ages, and the discovery of cosmic acceleration and the associated cosmological constant added age to the universe by changing the expansion history at late times, making the universe older at a given expansion rate than a matter-only model predicted. No single component of that resolution was dramatic. Each adjustment was modest and within the existing framework. But the combination of modest adjustments from multiple directions was sufficient to resolve the tension without requiring new fundamental physics. The lesson is that tensions can resolve through accumulation of small corrections rather than through single large revisions, and that patience and attention to systematic errors across multiple lines of evidence is often rewarded with resolution rather than revolution. The oxygen claim at z equals 14 is most naturally evaluated in light of this history. The most likely resolution is probably not a fundamental revision of lambda CDM's cosmological framework. The most likely resolution is a combination of a somewhat revised redshift from better spectroscopic data, a more nuanced physical interpretation of the emission line that reduces the implied metallicity, a better theoretical model of early star formation that accommodates rapid enrichment within the existing framework, and improved characterization of the systematic errors in the current measurement. None of these components individually would be dramatic, but their combination could bring the observation and the theory into better agreement without requiring new fundamental physics. That does not mean fundamental new physics is impossible. It means it is not required by the current evidence, and science should not invoke it until it is required. The principle of parsimony, which in cosmology translates to testing astrophysical explanations before cosmological ones, is a practical guide that has served the field well. When an observation appears to challenge the cosmological framework, the first question should be whether it can be explained within the existing framework by allowing for astrophysical processes that are not well captured by current models. Only when astrophysical explanations are exhausted or clearly inadequate should the investigation turn to modifications of the cosmological framework itself. Applied to the oxygen claim, the astrophysical explanations that have been explored include top-heavy initial mass functions, bursty star formation, dense environments, rapid recycling of stellar ejecta, and nuclear activity that enhances emission line strength without implying high metallicity. None of these explanations has been definitively confirmed or ruled out for this specific object. The investigation of which astrophysical explanation best fits the data is ongoing, and the answer will not be fully clear until better spectroscopic data are available. In the meantime, claiming that the observation requires new cosmological physics would be premature and would short-circuit the systematic exploration of astrophysical alternatives that is the appropriate first step. The history also teaches that the most productive attitude toward frontier results is a combination of genuine engagement and calibrated skepticism. Genuine engagement means taking the results seriously enough to invest resources in testing it, developing theoretical interpretations of it, and designing observations that can discriminate among those interpretations. Calibrated skepticism means maintaining awareness of the known failure modes of the methods used, insisting on independent confirmation before drawing strong conclusions, and resisting the temptation to overinterpret a single result as definitive evidence for or against any broad theoretical claim. The scientific community's response to the oxygen claim has largely embodied this combination. The initial report generated immediate interest and motivated multiple groups to analyze the data independently and to propose follow-up observations. Theoretical papers appeared quickly exploring the physical conditions that would be needed to explain the detection and testing whether those conditions are plausible within existing models. Critical analyses pointed out potential systematic errors and alternative line identifications. The combination of engagement and skepticism has been productive, generating a richer understanding of what the observation implies and what its limitations are. What has not yet happened is the definitive confirmation that would move the claim from provocative to established. That confirmation requires either additional spectroscopic data on the same object that strengthens the detection of the claimed feature and reveals additional corroborating features, or independent detection of the same feature by a different team using different analysis methods, or observations that rule out the alternative interpretations with sufficient confidence. All of these paths are being pursued, but none has yet reached its destination. The investigation is in its productive middle phase, where the initial excitement has given way to the careful systematic work that will eventually produce resolution. The productive middle phase of a frontier investigation is often the least publicly exciting, but scientifically the most important. It is where the systematic errors are characterized, where the alternative interpretations are tested and excluded or confirmed, and where the theoretical models are refined to make predictions specific enough to be falsifiable. This phase is slow because it requires accumulating data and performing analyses that are technically demanding and time-consuming. It is also the phase where the community's collective judgment is most valuable because individual researchers can lose perspective on specific aspects of a problem that they have been immersed in for a long time. The community judgment is expressed through the peer review process, through conference presentations and discussions, through replication of analyses by independent groups, and through the informal communication channels that connect researchers working on related problems. Each of these mechanisms has its limitations and its biases, but together they provide a filter that separates results that are robust from those that are not. The oxygen claim has been subjected to this filter to a significant degree, but not yet comprehensively. As more researchers engage with the data and the analysis, the filter will become more complete, and the confidence in the result will either rise or fall accordingly. The timeline for that comprehensive evaluation is uncertain but not indefinite. The pace of progress in high-redshift observational astronomy has accelerated dramatically with Webb's operation, and the community is producing and evaluating results at a rate that would have seemed extraordinary just a few years ago. The combination of rapid publication, open data release, and active community engagement through workshops and conferences is compressing the timeline for evaluating frontier results compared to earlier eras. What might have taken a decade to resolve in the pre-Webb era may now be resolved in a few years, not because the science is less rigorous, but because the tools and the community infrastructure for doing it are more capable. The expectation, based on the pace of current progress, is that the fundamental question about the oxygen claim will be substantially resolved within the next 3 to 5 years. Within that timeframe, additional spectroscopic data from Webb will either strengthen or weaken the detection. Independent analyses will either confirm or revise the redshift estimate. Theoretical models will either accommodate or be strained by the observation. And the broader population context will either identify similar objects that support the reality of early chemical enrichment or fail to find them in ways that suggest the claimed detection is unusual rather than typical. The combination of these developments will produce a picture that is much clearer than the current one, even if it is not yet perfectly sharp. In anticipation of that resolution, it is worth considering what each possible outcome would mean for the broader understanding of the early universe and for the field of cosmology. if the oxygen detection is confirmed at Z equals 14. 32. The immediate consequence is that early chemical enrichment is a real physical phenomenon that occurs faster than standard models of early galaxy formation predict. That conclusion demands revision of those models, specifically of the assumptions about star formation efficiency, initial mass function, and metal retention in early halos. The revision would be astrophysical rather than cosmological in the first instance, modifying the recipes for galaxy formation within the existing lambda CDM framework rather than modifying the framework itself. The astrophysical revision would have cascading consequences for predictions of other early galaxy properties. If star formation is more efficient and enrichment is faster than current models suggest, then the stellar mass density at high redshift should also be higher than current models predict. The luminosity function at extreme redshifts should be brighter and perhaps more extended toward high luminosities. The chemical abundance patterns in the most metal-poor halo stars of the Milky Way might need to be reinterpreted in light of a more efficient early enrichment scenario. And the predictions for the 21-centimeter signal from reionization might need to be revised because more efficient early star formation would produce more ionizing photons and potentially accelerate reionization. Each of these cascading consequences is itself testable with current or near-future observations, which is precisely what makes the confirmation of the oxygen claim scientifically valuable beyond the immediate result. A confirmed early oxygen detection would not just add one data point to the catalog of known high-redshift galaxies. It would trigger a cascade of investigations across multiple subfields of astrophysics and cosmology, each of which would produce new understanding and new questions. Science advances through exactly this kind of cascade, where one confirmed surprising result opens new fronts in multiple directions simultaneously. If the oxygen detection is confirmed at Z equals 14, 32 and the astrophysical revisions prove insufficient to accommodate it within lambda CDM, the second-order consequence would be to turn attention toward the cosmological framework more seriously. This would involve testing whether the abundance of such galaxies is consistent with the halo mass function predicted by lambda CDM, whether the implied growth rate of structure is consistent with the CMB-derived parameters, and whether any modification of those parameters can accommodate the observations without violating other well-established constraints. This is a harder and longer process than the astrophysical revision, and it would require the kind of multi-line convergence that marked the acceptance of cosmic acceleration before it could reach a conclusion. If the oxygen detection is revised to a lower redshift by future spectroscopy, the immediate consequence is less dramatic but still scientifically instructive. A galaxy at Z equals 10 or 12 with detectable oxygen is still a chemically enriched early galaxy that requires early star formation, even if the timeline is less compressed. The physical mechanisms invoked to explain rapid enrichment would still be relevant, but the constraints on them would be less severe. The investigation would shift from explaining enrichment in 290 million years to explaining it in 500 million or 600 million years, which is a different and less extreme challenge. The broader questions about early galaxy formation would remain relevant, and the methods developed to address the extreme claim would remain useful. If the spectral feature identified as oxygen is reinterpreted as something else at a lower redshift, the consequences depend on what the correct identification turns out to be. A lower redshift galaxy with different emission lines would be scientifically interesting in its own right, potentially revealing something about the population of unusual lower redshift galaxies that can mimic high redshift photometric signatures. The systematic lesson about how to avoid such misidentifications would be valuable for future analyses of the growing catalog of high redshift candidates, and the investigation would have produced a better characterization of the specific failure modes of high redshift spectroscopic analysis that can be applied to future observations. If the entire detection turns out to be a systematic error in the data or the analysis, with no real spectral feature at the claimed wavelength, the consequence is primarily a lesson in how to handle data at the detection limit. Such lessons are not failures of science, but contributions to the methodology of frontier astronomy. Every significant systematic error that is identified and corrected makes future analyses more reliable and makes future claims more credible. The history of astronomy is full of such lessons, and the field is stronger for having learned them, even when the learning was uncomfortable. In each of these possible outcomes, the investigation itself has value independent of where it leads. The questions it has raised about early star formation, chemical enrichment, and the reliability of extreme high redshift measurements have motivated productive work across multiple research communities. The observations it has driven will produce data sets that will be valuable for studying the early universe regardless of whether the specific oxygen claim survives scrutiny. And the theoretical models developed to evaluate the claim will be applicable to future observations of high redshift galaxies, even if the specific galaxy that motivated them turns out to be less extreme than initially thought. This is the way productive science works at the frontier. Individual results are provisional and subject to revision, but the investigations they motivate produce lasting value. The oxygen claim at Z=14 is a result of exactly this kind. Whether it survives in its current form or is revised by future data, its investigation is advancing the understanding of the early universe in ways that will persist long after the specific claim has been resolved. That persistence is the measure of scientific value at the frontier, not the longevity of any individual claim, but the depth and productivity of the investigation it motivates. Having surveyed the history and the epistemological landscape, the story must now address the human dimension of the investigation, because science is not only a system of methods and measurements, but a human activity carried out by researchers with careers, collaborations, and commitments. The oxygen claim was made by people working at the frontier of their field, and understanding the human context is part of understanding how the investigation will proceed and how it will eventually resolve. The researchers who reported the oxygen detection at Z=14 are working in one of the most exciting and most demanding environments in contemporary science. The pace of Webb discoveries has been extraordinary, with new results appearing at a rate that challenges the community's ability to absorb and evaluate them. The combination of unprecedented sensitivity, new wavelength coverage, and a rich early universe waiting to be observed has created a flood of data that requires rapid analysis and rapid publication to keep up with the pace of discovery. In that environment, the pressure to report results quickly can sometimes compete with the imperative to characterize them thoroughly before publication. The tension between speed and thoroughness is not new in observational astronomy, but it has been intensified by the Webb era. The telescope's capabilities are so far beyond its predecessors that almost every observation reveals something unexpected, and the community naturally wants to share those discoveries as quickly as possible. The audience for Webb results extends far beyond the professional astronomical community to include the broader scientific public, funding agencies, and policymakers who have invested in the telescope and who are eager for evidence that the investment is paying off. That broad audience creates a demand for results that can be communicated simply and dramatically, which can sometimes push toward overinterpretation of ambiguous data. The oxygen at Z=14 story has elements of this dynamic. The claim is dramatic, scientifically consequential, and easily communicated. It speaks to fundamental questions about the origins of the chemical elements that resonate with a broad audience. The combination of drama and fundamental significance makes it attractive as a headline result, and the incentive structure of modern academic science rewards results that generate attention and citation. None of this means the researchers who made the claim were motivated by anything other than genuine scientific curiosity and the desire to share an important finding. But it is worth acknowledging that the environment in which the claim was made has features that can push toward premature reporting, and that awareness of those features is part of responsible evaluation. The peer review process that governs publication of scientific results is designed to catch premature or overinterpreted claims before they reach the literature. When a paper claiming oxygen detection at extreme redshift goes through peer review, the reviewers are charged with evaluating whether the evidence is sufficient for the claims being made and whether the alternative explanations have been adequately considered. In principle, this process should catch the most significant problems before publication. In practice, peer review has limitations. Reviewers are experts but not omniscient, and they cannot always detect subtle systematic errors that require independent reanalysis of the raw data. The review of observational papers at the frontier is particularly challenging because the methods and the data are not always fully reproducible by reviewers who lack access to the original pipeline and calibration files. Open data policies, which are increasingly required by major funding agencies and journals, partially address this limitation by making the raw data available for independent analysis. Webb data is subject to a proprietary period during which the original observing team has exclusive access, followed by public release through the Mikulski archive for space telescopes. After public release, any researcher can download and analyze the data independently, providing a form of post-publication peer review that can identify systematic errors or alternative interpretations that the original team missed. This process takes time because independent analysis requires expertise and resources, but it is an important check on the reliability of frontier results. Several groups have already conducted or are planning independent reanalyses of extreme high redshift candidates from Webb, and those reanalyses have in some cases confirmed, and in other cases revised the original claims. The existence of this independent reanalysis effort is itself a sign of healthy community engagement with the results, and its outcomes will be valuable regardless of their direction. Confirmed independent reanalysis strengthens confidence in the original claim. A revised independent reanalysis identifies specific analysis choices that affected the result and provides guidance for future investigations. Either outcome advances the field. The collaborative nature of modern astronomy also plays an important role in how frontier results are evaluated. Large observational programs typically involve teams of tens to hundreds of researchers with different expertise, and the internal review within large collaborations can be as rigorous as the external peer review process. When a result emerges from such a collaboration, it has already survived scrutiny from multiple internal experts before it reaches the broader community. The oxygen claim was made by a team with expertise in high redshift spectroscopy, and the internal review process within that team presumably identified and addressed many potential concerns before the result was submitted for publication. That internal review is not a substitute for independent external analysis, but it is a meaningful quality control step. The relationship between individual researchers and the broader community is also shaped by career incentives that can create tension between ideal scientific behavior and practical necessity. Young researchers at early career stages have strong incentives to publish significant results quickly because their careers depend on establishing a record of productivity and impact. Senior researchers have incentives to maintain their reputations for sound judgment and reliable results, which can create caution that sometimes works against rapid publication of uncertain frontier results. The balance between these competing incentives within any research group affects how conservative or aggressive its publication strategy is at the frontier. The oxygen claim, like all frontier results, was made by researchers navigating these incentive structures as well as the scientific uncertainties. Understanding that navigation is not a criticism of any individual. It is an acknowledgement that science is a human activity shaped by human motivations, and that good institutional design of incentives and norms can make that activity more reliable and more self-correcting. The ongoing discussion within the astronomical community about appropriate standards of evidence for extreme high redshift claims is part of that institutional design process, and it will shape how future frontier results from Webb are reported and evaluated. The discussion has already produced some practical consequences. Several major journals have tightened their requirements for photometric redshift claims at extreme redshifts, requiring more rigorous documentation of alternative low redshift solutions and more careful treatment of selection effects. Conference presentations of frontier results are increasingly accompanied by explicit caveats about systematic uncertainties and the provisional nature of the conclusions. And the community norm of waiting for spectroscopic confirmation before drawing strong physical conclusions from photometric redshift estimates has been reinforced by the experience of seeing several high-profile photometric claims revised when spectroscopy arrived. These institutional adjustments are the appropriate response to an environment where the data are coming faster than the community can fully evaluate them. They represent the collective wisdom of a field that has learned from its history and is trying to apply those lessons in real time. The result should be a body of Webb results that, while emerging quickly, is more reliably characterized and more clearly qualified than it would have been without those adjustments. The oxygen claim falls within this context of institutional adjustment, and its ultimate fate will be partly determined by how well the current norms of the field are applied to its evaluation. The international dimension of the investigation is also worth noting. The research teams working on extreme high redshift galaxies with Webb are drawn from institutions across many countries, reflecting the global nature of modern astronomical research. The coordination among these teams, through data sharing, joint analysis efforts, and coordinated publication strategies, is essential for avoiding duplication of effort and for ensuring that independent analyses are truly independent. When two groups that shared raw data or analysis code find consistent results, their agreement is less convincing than if they had worked completely separately. True independence requires starting from the archived raw data and conducting all aspects of the analysis from scratch, including the calibration, source extraction, spectral extraction, and line identification. Achieving true independence is difficult in practice because the relevant expertise and software tools are concentrated in a small number of groups that inevitably interact at conferences and through publications. But the aspiration toward independence is important for calibrating how much weight to give to confirmations that claim independence but may share unexamined assumptions. The most convincing confirmations are those that use demonstrably different methods and find consistent results, because different methods typically have different systematic errors that would not both conspire to produce the same incorrect answer. The investigation of the oxygen claim at z=14 will ultimately be judged by whether it meets this standard of multi-method independent confirmation. If it does, the claim will stand as one of the most remarkable discoveries of the Webb era. If it does not, it will serve as a valuable case study in how even sophisticated analyses at the frontier can be misled by systematic errors, and the lessons drawn from it will make future frontier analyses more reliable. In either case, the investigation is producing value for the field, and that value is independent of the ultimate fate of the specific claim. As the investigation continues and the evidence accumulates, the broader scientific community and the interested public are faced with the challenge of understanding a result that sits in a state of genuine and honest uncertainty. That uncertainty is not a failure of science to communicate clearly. It is the accurate communication of the actual state of knowledge at the frontier. The challenge is to convey that uncertainty in a way that neither dismisses the result as unreliable nor inflates it into a confirmed discovery, because both misrepresentations would ultimately undermine public understanding of how science works. The oxygen galaxy at z=14 is genuinely uncertain in a specific and quantifiable sense. The redshift has a measurement uncertainty that reflects the signal-to-noise ratio of the spectral data. The line identification has a probability of being correct that reflects the number of alternative identifications and their relative plausibility. The physical interpretation has a range of possible values for the oxygen abundance that reflects the model dependence of the inference. And the cosmological implications have a degree of challenge to lambda CDM that depends on which of those physical interpretations is correct. Each layer of uncertainty is real and documented, and the honest presentation of the result requires preserving all those layers rather than collapsing them into a single dramatic claim. The challenge of communicating calibrated uncertainty is not unique to astronomy. It arises in all fields where frontier research produces results that are important but not yet definitively established. The public communication of such results involves choices about emphasis, context, and simplification that can easily slide toward either dismissal or exaggeration. The most responsible communication acknowledges the significance of the question being investigated, describes the evidence that has been gathered and its limitations, explains what further evidence would be needed to reach a more definitive conclusion, and places the result in the context of related findings that provide additional perspective. For the oxygen galaxy, that responsible communication might describe the observation as a compelling candidate for the most distant galaxy with detectable oxygen, whose confirmation would have major implications for our understanding of early chemical enrichment, but whose current evidence is not yet sufficient to draw strong conclusions about whether it truly represents a challenge to existing models of galaxy formation. That framing is less exciting than declaring the discovery of impossible early chemistry, but it is more accurate and ultimately more useful for building public understanding of how science advances at the frontier. The relationship between scientific uncertainty and public communication is particularly fraught in cosmology because the subject matter is inherently dramatic. The early universe, the first stars, the origins of the chemical elements, and the large-scale structure of space and time are topics that naturally inspire wonder and that connect to fundamental questions about where we came from and how the universe works. That inherent drama makes cosmological results particularly appealing to science communicators and particularly susceptible to exaggeration by those who want to make the subject accessible and exciting. Exaggeration in science communication has costs beyond the immediate inaccuracy. It builds expectations that real science cannot consistently meet, because real science advances through careful accumulation of evidence that is rarely as dramatic as a simplified headline suggests. When the headline result turns out to be more nuanced than advertised, public trust in science can erode, not because the science failed, but because the communication created unrealistic expectations. The most durable public understanding of science is built on accurate communication of uncertainty and of the process by which uncertainty is resolved, even if that communication is less immediately exciting than a bold claim of discovery. The oxygen galaxy is an opportunity to model good science communication precisely because it is genuinely uncertain and genuinely important. By explaining what is known, what is uncertain, what further observations would clarify, and how the community is working to evaluate the claim, communicators can convey both the excitement of frontier research and the rigor that makes its conclusions reliable. That combination is the most accurate and the most useful picture of how science actually works, and it is a picture that serves the public interest better than either dismissive skepticism or uncritical enthusiasm. In the end, the story of the oxygen galaxy at z=14 is a story about the current state of human understanding of the early universe. It is a story about remarkable technology that can collect ancient photons and read in them the signatures of elements forged in stars that died more than 13 billion years ago. It is a story about the physical processes that turned the formless simplicity of the Big Bang into the chemical complexity of stars, planets, and life. And it is a story about the careful, patient, rigorous process through which human beings figure out whether their measurements of that ancient chemistry are telling them something new about the universe, or something new about the limitations of their instruments and methods. The cosmic clock at the heart of this story is not just a technical tool for converting redshifts into ages. It is a symbol of humanity's ambition to understand its own origins in cosmic terms. When we measure the age of the universe at which a distant galaxy emitted the light we are now receiving, we are performing an act of temporal empathy with the early cosmos, reaching across billions of years to ask what was happening when the universe was young. The oxygen claim is an answer to that question, tentative and uncertain, but genuinely posed and genuinely investigated. Whether the answer is confirmed or revised, the act of asking it is itself significant. It reflects the remarkable position that humanity now occupies, equipped with instruments and methods sophisticated enough to detect the chemical fingerprints of individual elements in galaxies that existed when the universe was less than 3% of its current age. That capability did not come easily or quickly. It was built over decades through the contributions of thousands of researchers, engineers, and administrators who collectively made Webb possible. And it is being exercised through the work of the current generation of astronomers who are turning Webb's photons into knowledge about the earliest chapter of cosmic history. The oxygen in the spectrum of a galaxy at the edge of the universe is a thread that connects the present to the beginning, the local to the cosmic, and the chemistry of life to the physics of the first stars, whether that thread is as long as z=14. 32 suggests, or somewhat shorter, is a question that will be answered by the next generation of observations. But the thread itself, the connection between chemical complexity and cosmic origins that the investigation represents, is real and enduring regardless of where the final measurement lands. That enduring connection is what makes the investigation worthwhile and what makes the uncertainty productive rather than frustrating. The frontier of observational cosmology is where humanity's understanding of the universe meets its current limitations, and the productive tension between what we know and what we do not know is the engine that drives the field forward. The oxygen galaxy at z=14 sits exactly at that frontier, making it not just an object of study, but a marker of where we currently stand in the long project of understanding the universe from its beginning to its present and toward whatever future awaits it. The investigation continues, the evidence accumulates, the understanding deepens. And the cosmic clock ticks on, marking time in a universe that began in simplicity and has spent 13.8 billion years building the complexity that includes the observers who are now looking back at its first light, trying to read in a faint infrared spectrum the story of how it all began. There is one final dimension of this story that deserves attention before it closes. The oxygen claim and the broader program of early universe observation with Webb are connected to a question that extends beyond the technical details of spectroscopy and cosmological modeling. They are connected to the question of what the existence of chemical complexity so early in the universe's history means for the broader question of cosmic habitability and the distribution of life in the universe. The oxygen in the spectrum of the z=14 galaxy, if real, is the same element that fills the lungs of every person who has ever breathed. It was forged in the cores of massive stars, distributed by their explosive deaths, recycled through subsequent stellar generations, eventually incorporated into the molecular cloud that formed the Sun, distributed through the solar nebula, and concentrated in the rocky material that became Earth. The oxygen we breathe is the product of a chemical history that spans the age of the universe, and that began, potentially, with events like those occurring in the galaxy at the edge of the observable cosmos. The implications of early chemical enrichment for cosmic habitability are profound. If the universe was building oxygen-rich environments within the first few 100 million years after the Big Bang, then the raw materials for rocky planets, and potentially for life, were being assembled much earlier than the standard picture of gradual hierarchical enrichment would suggest. Early galaxies with detectable oxygen represent early opportunities for the chemistry that underpins life as we know it, even if the specific conditions needed for life to emerge require additional time and refinement beyond simple oxygen availability. The concept of the cosmic habitable zone in time, analogous to the habitable zone in space around a star, describes the epoch during which the universe is sufficiently chemically enriched to support rocky planets and complex chemistry, but not so old that it is running out of stellar fuel and degenerating toward a dark and cold future. The evidence that oxygen appears very early in the universe's history, if confirmed, would push the beginning of the cosmic habitable zone earlier than current estimates suggest, potentially extending the timeframe during which life could emerge and persist across cosmic history. This is not merely a speculative philosophical point. It has specific observational consequences for the search for biosignatures in exoplanet atmospheres and for the interpretation of the distribution of complex organic chemistry in the interstellar medium. If the chemical prerequisites for life were assembled earlier in cosmic history than expected, then the probability that life-bearing planets exist in the ancient stellar populations of old elliptical galaxies and globular clusters might be higher than standard models of chemical evolution would suggest. Those environments have been dismissed as unlikely habitats partly because their stellar populations are old and metal-poor, reflecting enrichment that began early but proceeded differently from the star-forming galaxies, where most rocky planet formation is expected to occur. The oxygen detection is not direct evidence for life. It is not even direct evidence for rocky planets, which require additional elements including silicon, iron, and magnesium in specific ratios. But it is evidence that the chemical building blocks of potential habitability were being assembled in the early universe, and that the window of cosmic habitability may be wider and earlier than previously thought. That wider window has implications for the Fermi paradox, for the distribution of technological civilizations in the universe, and for the long-term future of intelligence and complexity in the cosmos. These implications should be held lightly given the uncertainty of the oxygen claim itself. Extrapolating from a single uncertain spectral feature to conclusions about the prevalence of life in the universe requires many steps of inference, each of which introduces additional uncertainty. But the connections are real and worth noting as part of the broader significance of the investigation. The reason humanity invests in telescopes like Webb is not only to resolve specific technical questions about redshifts and emission lines. It is to understand the universe's history as a whole, including the history of how the conditions for life were assembled and how those conditions are distributed across cosmic time and space. The oxygen galaxy at Z equals 14 is, in that sense, a data point in the investigation of those ultimate questions. It sits at the intersection of the smallest scales, the atomic physics of oxygen emission, and the largest scales, the cosmological expansion that converts its light into a time stamp. It connects the present to the beginning through a chain of physical processes that spans every order of magnitude in scale and complexity that the universe contains. And it poses in the specific and technical language of spectroscopy and cosmology one of the oldest and deepest questions that curious beings have ever asked. How did the universe build the complexity we see around us and inside us? How did simplicity become richness, uniformity become structure, and emptiness become the chemically elaborate world we inhabit? The answer lies in the light of ancient galaxies, in the spectra of stars that died billions of years ago, and in the patient, careful, rigorous investigation of measurements like the one at the center of this story. The oxygen claim is one thread in that answer, uncertain but not unimportant, provisional but not trivial, and part of a larger tapestry that humanity is still weaving, one photon at a time, from the light of the distant universe. The investigation continues. And in its continuation lies the best hope of understanding not just what the universe contains, but how it came to contain it, and how the chain of events that began with the Big Bang and passed through the first stars and the first galaxies eventually produced observers capable of looking back at that beginning and trying to read in its faint infrared light the story of how everything began. That is what the thin line in the spectrum is about, not just oxygen, not just a redshift. but the universe telling its own story in the only language it has, which is the language of light, and humanity learning, slowly and carefully, how to listen.